Good morning, everybody. This is Masato Takita, the moderator today from ICRR, that is Institute for Cosmic Ray Research, UTokyo. This program, entitled Exploring the Universe with Multi-Messengers, is adopted by UTokyo as UTokyoNY Event, which is held in cooperation with UTokyo New York office. Well, as I speak in English, the official language is English at this event. First of all, Professor Hiroyuki Sagawa from ICRR, the chairperson of this event, will give an opening remark. Professor Sagawa, please.
Good morning, everyone in New York, and good midnight, everyone in Japan, and to the participants in the rest of the world. Today, we are holding one-day public symposium titled Exploring the Universe with Multi-Messengers. This symposium is organized by the Institute for Cosmic Ray Research with the cooperation of the New York office. Thus, this symposium is held in commemoration of the renovation of the New York office. After me, the president of University of Tokyo New York office, Masaharu Masiyama, will talk about the New York office. And we invited the president of Simons Foundation, Professor David Spiegel, for guest speech. Professor Kajita, the director of ICRR, will introduce our institute, ICRR. We will have keynotes by Professor Kajita and Dr. Peter Fritschel. And 4 ICRR professors will give presentations on their experiments. There will also be invited speakers in the United States in the related fields. This symposium was initially planned to be held from New York as the main venue together with online mode. But due to COVID-19 situation, we have decided to hold this symposium completely online. For posters and your mutual interactions, we also set up virtual space called Gather Town, where you're welcome to use during lunchtime and break. And let me tell you that the number of registrants of researchers and the general public has exceeded 300. So I would thank all of you for your interest in this symposium. I hope you will enjoy the symposium. Thank you.
Thank you very much. Then please watch an introduction video to UTokyo New York office.
Welcome to the University of Tokyo New York office. The office is located in Midtown Manhattan, which is also in a business district where many Japanese U.S. headquarters and U.S. companies are located. Such prime locations enables us to serve as a networking platform for Japanese and American institutions here in North America. New York and its surrounding cities are home to many world-renowned universities. So the office can also act as a central location for extensive academic collaborations in North America. The University of Tokyo New York office was established in 2015 to facilitate research, academic, and social collaboration activities in the United States. The office is currently operated as a local affiliated entity, which can be utilized by the University of Tokyo. After undergoing major renovations in 2020, the office now houses the New York Office Salon, a new open space for seminars and workshops. This space beautifully reflects the university's spirit of knowledge that is open to the world and features astonishing knowledge shelves that embody the idea of sustainability, which is uniquely rooted in Japanese culture. We are truly excited to have this futuristic office where all stakeholders can get together in the heart of New York City. The New York office will serve as a communication hub for the University of Tokyo and further enhance the university's presence in North America through the use of these facilities. So far, while working closely with alumni, universities, and Japanese companies in the area, the New York office has held various events to disseminate the university's educational and research activities. Raising awareness will help us serve as a platform for study abroad programs and strengthen our partnerships with universities and research institutions in this country. In the future, we will use the New York office as a backbone for forming an integrated international network with other overseas offices of the University of Tokyo, conducting fundraising on a global scale, and developing innovative worldwide activities. Your gifts, which are greatly received with thanks, will be graciously used to support our students and researchers. We will continue to hold a variety of events to provide updates to our friends in the US and other countries about the progress and achievements in research at the University of Tokyo. The New York office is committed to advancing the university's mission of providing excellence in research and teaching to the global community. Stay involved, and we look forward to welcoming all of you to the office in person or online.
Now, we would like to have greetings from Mike Masiyama, the president of University of Tokyo, New York office.
Good morning, everyone. This is Mike Masiyama, the president of the University of Tokyo, New York office. Today's event is being held online and can be participated remotely by viewers from many parts of the world, and I thank you, those remote participants, for being with us. Also, I'd like to offer my heartfelt thanks to the Institute for Cosmic Ray Research and all other supporting institutions to hold this event at our office. This event is one of the annual programs of UTokyo, New York, and I'm pleased that Institute for Cosmic Ray Research chose our office space as the venue of this very important event. As seen in the introductory video shown earlier, the University of Tokyo, New York office was established in 2015 with the aim of promoting university's objectives of enhancing its international research, education, and community activities. This office was established as an independent non-profit organization of the University of Tokyo and can be utilized by all departments of the university. We underwent a substantial renovation of this office in 2020 to transform it into a more futuristic and efficient space where we can hold seminars and workshops more handily. And now I'm speaking from this renovated office. The annual UTokyo New York events are designed to help create networks among UTokyo alumni and researchers resided in the US to advocate for the research activities of the university and to establish a good support structure for its research in the US. It was my hope to hold this event here in New York in person, so I could show you this office, but I want you to feel at home participating in today's remote event. But I hope you can visit us in person in the near future. UTokyoNY is a non-profit organization, and its activities are supported by generous donations from people like you. Your support is very important for us to pursue our mission to enhance the presence of the University of Tokyo in the US and furthering US-Japan academic exchange. We appreciate your understanding and your monetary contributions to UTokyoNY, which are normally tax-deductible in the US. I urge you to visit our website by Googling University of Tokyo, New York, and find more about our activities, past and future. You can also find a Make a Gift button there to make your donations online. Last but not least, I sincerely hope that today's event would enhance mutual communications among the researchers and participants and would be fruitful to all of you. Thank you very much.
Thank you very much. Next, we would like to have greetings from David Esparya, the president of Simons Foundation. Now, President Esparya, please.
So I'd like to begin by welcoming everyone to New York. I am here, actually a mile away from the University of Tokyo office at my office on 5th and 21st Street, and start by just encouraging people to come and visit New York. I regret that conditions were such that the decision was made to go on Zoom. Just so people know what conditions are here, case numbers have now dropped by a factor 30 from the peak. Unlike other parts of the United States, adults in New York are 95% vaccinated. I checked the number this morning. And most importantly, activities are fully back. I saw Come From Away on Broadway last night. I have tickets to see Six, the story of Henry VIII's wives, tonight. And we'll be eating inside for dinner with my family at a large event on Sunday night. So things have indeed returned to normal. I look forward to an exciting workshop on multi-messenger astronomy. This is an exciting topic, and with many leaders in this field, from cosmic rays to gravitational wave physics to theoretical modeling, located either in New York or in the New York region, or located at University of Tokyo. So it's a very timely subject. I thought I would use my brief remarks actually to talk a little bit about my own interactions with University of Tokyo over the years. Before becoming president of the Simons Foundation, I was a professor at Princeton for over 30 years and department chair for over a decade. We had built and continue to have a very strong relation with University of Tokyo, one that began back in the 1980s with Ikeuchi-san's visit to Professor Jeremiah Ostraker, and strengthened significantly by my colleague, Professor Ed Turner, who had made frequent visits to Japan and continues to do so. Those connections helped build the Japanese participation group in the Sloan Digital Sky Survey, a group that made very important contributions to this transformative survey that really helped change the way we do astrophysics. It really shifted it from the big telescope mode of doing astronomy to a quantitative statistical astronomy approach. And this is an area where Suto-san at University of Tokyo played an important role in guiding and building up these programs. Over the years, there have been a number of University of Tokyo-led collaborations, the SEEDS collaboration to study exoplanets, the ongoing Hyper Supreme Cam survey using the Subaru telescope, which is now the deepest large area survey of the sky, is led out of University of Tokyo with significant participation from Princeton and other institutions in the United States. And now the prime focus spectrograph on the Subaru telescope is about to be the premier spectroscopic instrument for studying large-scale structure in the world and studying the evolution of galaxies. This is a University of Tokyo-led project with significant participation from Caltech, Hopkins, Princeton, Taiwan, really universities throughout the world. Not only have we worked together on projects, we have benefited enormously from exchange of students and going really both ways. Miyatake-kun, a PhD student from Tokyo, came to Princeton as a JSPS postdoc to work with me for several years. He has now returned to Japan as a faculty member. Keegan Lee, one of my former PhD students, is now faculty at KIPMU. So to me, this relationship where we've connected on projects, on students, and really have helped work at the forefront of science together over the years, I see as a model for international collaboration. Now let me briefly put on my hat as president of the Simons Foundation. The Simons Foundation is one of the leading foundations in the United States supporting basic research in areas like math, physics, computer science, oceanography, and also in autism research. We have a budget of over $600 million a year that is primarily directed to grant supporting research, and a significant fraction of our efforts go towards supporting international scientific collaborations in various forms. And encourage you to visit our web pages to get a broader sense of the wide range of things we support. We are active not only in supporting science, but also in supporting education and outreach through things like Quantum Magazine and our film program. Our recent film, Fire of Love, was one of the successes at the Sundance Film Festival 2 weeks ago. Let me now return you to the program. But before doing so, just briefly put on yet one more hat I wear, which is chair of the IAU Committee on International Collaboration. And this is when we looked around, where were some of the greatest opportunities we felt for international cooperation on large projects. One of the areas that really stands out is multi-messenger astronomy, because it is an area where we will need, and we have been using a very wide range of instruments all across the spectrum, from cosmic rays to gamma rays to radio waves to gravitational waves. All of these studies are international. All of them are driven to neutrinos, driven by work all over the world. And these are areas in which University of Tokyo and many of the institutions in the New York area are leading institutions. And looking ahead at the program, there are some superb speakers, and looking forward to learning more at this meeting. So with only the regret that you're not here to join for coffee and lunch, look forward to hearing these talks. Thank you.
Thank you very much. Next talk is entitled Multi-Messenger Astronomy and ICRR, given by Professor Takaaki Kajita, the director of ICRR. Now, Professor Takaaki Kajita, please.
Thank you very much. Good morning and good evening, and maybe good afternoon. Well, it's an honor to speak in this symposium. So today I want to talk about multi-messenger astronomy and Institute for Cosmic Ray Research. Let me share my slide. Okay, I hope you see my slide. Okay, Okay, this is the outline of this talk. First, I have a brief introduction on multi-messenger astronomy and also about the Institute for Cosmic Ray Research. Then I would like to discuss the research projects that are carried out or will be carried out in Institute for Cosmic Ray Research. Gravitational wave Kagura, Gamma-Ray Cta, highest energy cosmic rays, telescope array or TA, cosmic rays and gamma rays, Tibet AS gamma experiment and Alpaca experiment, and neutrinos, super Kamiokande and hyper Kamiokande. And I'll summarize this talk. Okay, let's begin. Well, we are in the era of multi-messenger astronomy. We have several good examples. One is the detection of the merger of binary neutron stars. This is just one example. This shows the observed gravitational wave frequency as a function of time. So you see a signal that is increasing in the frequency. And by analyzing this data, we confirm the detection of the merger of binary neutron stars. And this detection by Ligo and Virgo, together with multi-wavelength electromagnetic observations, was one of the highlights in recent science. And these observations have told us many interesting results, such as the generation of heavy elements. So we are really excited. Another example is the detection of the high energy neutrino event, followed by gamma-ray observations. In the left, I copied the ice cube neutrino event, and in the middle, I show the Fermilab data. So clearly, Fermilab observed gamma-ray signals from the region indicated by ice cube. Also, MAGIC observed very high energy gamma rays from the same direction. So the detection of very high energy neutrinos by ice cube, together with multi-wavelength electromagnetic observations and the identification of the source object, that was Blazar, was another milestone event. So these examples indicate that we are entering the new era of multi-messenger astronomy. And we expect that many exciting discoveries are ahead of us. And of course, ICRR would like to contribute to the advancement of multi-messenger astronomy. Now, I'd like to briefly discuss the history of Institute for Cosmic Ray Research. In 1953, Cosmic Ray Observatory of the University of Tokyo was established. And here I show a rather old photo taken around 1960. And this was the photo of the Cosmic Ray Observatory at the Norikura Mountain. Then in 1976, Institute for Cosmic Ray Research of the University of Tokyo was established. In fact, ICRR was reorganized from the Cosmic Ray Observatory. Then I'd like to skip some history between 76 and 91. Anyway, in 1991, the construction of Super Kamiokande started, and the experiment started in 1996. In 1993, the construction of the Tibet AS Gamma experiment started. In 2003, the construction of telescope array, that is for the highest energy cosmic ray studies, started in Utah in the United States, and the experiment started in 2008. In 2010, the construction of Kagura gravitational wave project started. In 2018, the first Cta LST was constructed at La Palma, Spain. And in 2020, the construction of Hyperkamiokande started. So this is the brief history of ICRR. Now, let me summarize the ICRR related facilities. In Japan, of course, we have the ICRR headquarters here near Tokyo. And in Kamioka, we have Super Kamiokande neutrino detector. And also in the same mountain, we have the Kagura gravitational wave interferometer. In addition, we are constructing Hyperkamiokande detector in the nearby mountain. If we look at the facilities outside of Japan, we have telescope array experiment in Utah, Cta North and Magic in La Palma, Spain. Alpaca will be constructed in Bolivia. And finally, Tibet AS Gamma experiment in Tibet. So these are the ICRR related facilities, and various studies are carried out in these experiments or facilities. Now, I'd like to discuss each project. First is the gravitational wave, Kagura. First of all, let me show this slide. This is a summary of LIGO Virgo observations. So far, total of 90 gravitational wave events was observed, and most of them are binary black hole mergers, but there are several binary neutron star and neutron star black hole mergers. So I think we are really in an exciting time. Therefore, we'd like to contribute to the gravitational wave astronomy. And therefore, we are constructing the Kagura Interferometer. Kagura project was approved in 2010. And this is the sketch of the Kagura Interferometer. It is located in underground in Kamioka. Well, underground site is very important because in underground, the seismic noises are typically much smaller compared with those at the surface. Also, we are going to use cryogenic mirrors to reduce these thermal noises. This is the sketch of the Kagura optical configuration. But I'm afraid I cannot go into detail, but I would say overall, the Kagura optical configuration is very similar to LIGO and Virgo, except for cryogenic mirrors. and the cryogenic mirrors are installed in large cryostat, which is shown. One of them is shown here. Now, let me discuss the Kagura sensitivity history. Kagura has finished the installation in the spring of 2019. Then we started the commissioning work. And after a very intense commissioning period, Kagura started the observation in April 2020. Here, I show the improvement of the Kagura sensitivity. So compared with the sensitivity in August 2019 and March 2020, almost 4 orders of magnitude improvement in sensitivity was achieved. Anyway, we started the observation, but unfortunately, due to COVID-19, we stopped the operation in 2 weeks. Then what will be our plan? Well, okay, this slide summarizes the observation history and our plan. LIGO had so far O1, O2, and O3, and O4 will be starting at the end of this year. So Kagura will join O4 from the beginning, then start the cryogenic commissioning. Well, in this slide, anyway, start the cryogenic commissioning during O4 and rejoin O4 with reasonably high sensitivity, and we'd like to contribute to the gravitational wave astronomy. Now, you may ask, what will be the gain with Kagura? Well, certainly, we'd like to contribute to the gravitational wave astronomy, and in particular, we'd like to contribute in improving the sky localization. If we have Ligo and Virgo only, then for some directions, their sky localization is rather poor. But if we have Kagura with similar sensitivity, then we can improve the sky localization even for the directions that Ligo and Virgo cannot very precisely determine. So this way, Kagura would like to contribute to the gravitational wave and multi-messenger astronomy. Now let's move on to the gamma rays, Cta. Well, first of all, the motivation for the gamma ray studies. So we'd like to know the source for cosmic rays. Then the question is, how can we know the source of cosmic rays? Unfortunately, even if we very precisely determine the arrival direction of cosmic rays, we do not know the direction of the source because of the magnetic field in the universe. So we have to observe neutrinos or gamma rays. And therefore, we joined the MAGIC collaboration. This photo shows the 2 MAGIC telescopes. And well, MAGIC has produced very many important results. But let me show you just one example. This is the TeV emission from the gamma ray burst, GRB 1914C. So in this gamma ray, MAGIC observed a very high flux. And this high flux continued for more than 1,000 seconds. Also, the suggested spectrum is extending above 1 TeV. So this is the first unambiguous detection of TeV gamma rays from GRV. And we certainly expect much more in the near future. And in addition to the gamma ray burst, there are many sources that should be studied with these TeV gamma rays. I don't go into detail of these sources, but I just want to say there are many, many sources to be studied. And therefore, we joined CTA, in particular in the LST project in the north site. And this is the image of the CTA site in La Palma. But at present, there are 2 magic telescopes. In addition, the CTA1 is already constructed, and LST1 is already constructed, and LST2 to 4 will be constructed soon. And here I show some highlight. Well, inauguration of ceremony was held on October 10th, 2018. This is the first CTA LST. Then, since then, the team started the commissioning, and from the beginning of 2020, the team started the observation with LST1. And so far, about 500 hours of scientific observation was already carried out. So we expect exciting new results pretty soon. And this is the timeline of the CTA construction. CTA LST1 is in the commissioning and operation phase. And the deployment of LST2 to 4 will be between 2022 and 2024. And then there'll be an observation as 4 LST array from 25 to 28. Then observation will be made by observatory. So clearly, we are in the most exciting time, and we are expecting many exciting results from CTA. Now I'd like to move on to the highest energy cosmic rays telescope array. Well, this is the energy spectrum of cosmic rays. And we have a question. So far, we observed the energy spectrum up to 10 to 20 electron volt. So we'd like to know if this is the end of the cosmic ray energy spectrum. And also we'd like to understand how and where these cosmic rays are accelerated. To answer these questions, the telescope array was constructed. This is the map of the telescope arrays, surface detectors, plus fluorescence detectors. So by using surface detectors plus fluorescence detectors, they observe cosmic rays. In addition, they have tail, that is the low energy extension near MD's fluorescence detector site. And here, I just want to show you some highlights from TA. The left upper one shows the energy spectrum from TA and OJ. OJ is the highest energy observatory in the southern hemisphere. And you can see that there is some difference, some visible difference in the energy spectrum at the around 10 to 20 electron volt at the highest energy point. Well, there have been many discussions, but there are various studies going on with the OJ plus TA working group. For example, taking the common declination, then we realize that the difference gets much smaller. But in fact, this is actually one of them. They have much more detailed discussions. But anyway, we think that with time, we better understand the data. Furthermore, the anisotropy data are quite interesting. So depending on the threshold energy, there are visible anisotropy of statistically reasonably significant. So clearly the data are very exciting, and we expect exciting new results in the near future. So because of this exciting data, in particular the hotspot data, TA times 4, that is the extension of the surface coverage by factor of 4, that is 3,000 square kilometers, was proposed. And the TA4 is constructed. So far, well, not completed yet, but so far, 257 surface detector was installed. And also 2 new fluorescence detector stations were in operation. So we really expect new result from TA4, TA times 4, pretty soon. Now I would like to move on to the next topic, that is the cosmic rays and gamma rays, Tibet AS Gamma experiment and Alpaca experiment. Tibet AS Gamma experiment is a high altitude air shower experiment. And this is the sketch of the detector. And in particular, I'd like to mention the underground water Cherenkov muon detector. And with this, they were able to separate gamma rays from cosmic ray backgrounds. Therefore, by using the muon detector signal, or by using muon detector as the veto counter, they are able to observe sub-PeV gamma rays. And here, I just want to show one example. This is the distribution of gamma ray candidates after very tight muon cut. And clearly, there are many signals observed along the galactic plane. And in particular, these signals did not coincide with the known PeV gamma ray sources. So this is the evidence for galactic cosmic rays beyond PeV energies. Well, this was just one example, but they have another observation of the sub-PeV gamma ray sources. So these observations suggest that we are just starting the sub-PeV gamma ray astronomy. Now, Tibet AS gamma ray experiment produced very interesting results. However, of course, Tibet experiment is located in the north. On the other hand, in the southern sky, there should be much more gamma ray sources. Therefore, it's natural to start working in the southern hemisphere. Therefore, the new group is formed, and they would like to start the Alpaca experiment. That is an experiment similar to the Tibet AS gamma experiment. And in this year, they would like to start the Alpaca experiment. That is about 25% of the full Alpaca configuration. Also, they would like to continue the construction of the half Alpaca in this year and next year. Now, I'd like to move on to neutrinos. I'm afraid I spent too much time. Anyway, let me move on. Well, I'd like to discuss Super Kamiokande. Of course, Super Kamiokande is known for the studies of neutrino oscillations. But today, I want to talk about the supernova relic neutrinos. Well, this is the history of the universe. And in this history, supernova occurred. And in each supernova explosion, neutrinos are produced. Therefore, these neutrinos are still propagating in the universe, and they may come to the Super Kamiokande detector. So, Super Kamiokande wants to observe neutrinos produced by supernova explosions in the past universe. However, the flux is not very high. Therefore, they have to reduce the other neutrino background as much as possible. And to do so, they would like to observe the coincidence of observation of E plus and neutron. And of course, neutrons are invisible in water Cherenkov detectors. Therefore, they put gadolinium into the Super Kamiokande tank. And neutrons are absorbed by gadolinium, then gamma rays are emitted. And the total energy of the gamma rays are 8 MeV. Therefore, these gamma ray signals are visible. And this is the status and plans. First, in 2020, they put 0.01% gadolinium into the Super Kamiokande tank. Since then, they are taking data, checking water transparency and neutron capture efficiency and so on. Then in the spring to summer, they would like to increase the gadolinium concentration to 0.03%. With this concentration, the neutron capture efficiency will increase to 70%. And they would like to start long-term observation in this year. And the expected number of supernova relic neutrino events is about 5 to 13 in 5 years. So they would like to observe these neutrinos in 5-year timescale. Finally, I want to briefly discuss Hyperkamiokande. Hyperkamiokande is a very large water Cherenkov detector, which is about 8 times larger than present Super K. In addition, Hyper K will be exposed to the 1.3 megawatt JPAC neutrino beam. Anyway, this detector will have many important research topics in neutrino physics and astrophysics. The construction is already started. The experiment will start in 2027. And as for the neutrino astrophysics, I just want to mention the supernova neutrino burst detection. Thanks to its very large mass, Hyperkamiokande will observe many neutrino events. For example, if a supernova explodes at the galactic center, about 100,000 events will be observed. And with these many events, Hyper-K can distinguish between different explosion models. Furthermore, multi-messenger observation with gravitational wave and electromagnetic telescopes should be very important to really understand the supernova explosion mechanism. Okay, let me summarize. Very exciting multi-messenger astronomy is starting, and we'd like to contribute to the multi-messenger astronomy in Institute for Cosmic Ray Research. Okay, that's all. Thank you very much.
Thank you very much. Now, the session is open for questions and comments. Any questions, comments? Please write questions or comments in the chat in Zoom or write in Slido in YouTube. I will pick some up and read them aloud. Well, we have already 3 questions. One by one, I would like to ask Professor Kajita. The first question, what were you impressed by Dr. Koshiba Masatoshi's attitude? Please.
Okay, thank you very much. I didn't expect this question. Well, certainly, I was definitely influenced by Professor Koshiba. He's very strong in doing what he wanted to do. So also, he was a very good mentor to students, and he always encouraged us to think about our own experiment. Maybe, is it okay?
Yeah. Thank you. And the second question. Well, the COVID-19 pandemic, well, is it creating any new opportunities for the future research and scientific development of the ICRR?
Thank you for this question. Well, I'm afraid, well, I don't recognize any new opportunities. Instead, we have damaged by COVID-19 in many ways. We are unable to travel to facilities outside of Japan. Also, many collaborators cannot come to Japan. Therefore, inevitably, our speed in research is slowed down. Definitely, we would like to get speed after the COVID-19.
Thank you. And finally, the third question. The research activity of ICRR, are they useful for resolving social, ecological, and climate problems?
Thank you for this question. Unfortunately, I'm afraid we may not be able to contribute substantially to these questions. We are interested in understanding the universe.
Thank you very much. Any other questions, comments? If not, we would like to thank the speaker again. Thank you very much, Professor.
Thank you.
Well, then let's move to the next talk. The next talk is entitled Gamma-Ray Observation at La Palma, Spain, Cherenkov Telescope Array, given by Professor Masahiro Teshima from ICRR. Now, Professor Masahiro Teshima, please.
Yes, thank you very much. Can you hear me?
Yes, very
Okay.
clearly.
Yeah. Let me share my slide. Okay. So I want to discuss about the Gamma-Ray Astronomy at the La Palma, the Cta project, essentially Cta project, and especially the large size telescope, LST project. I'm acting as a PI of this Cta LST project. And you can see a nice picture of this is a montage, photo montage. You can see two magic telescope, white telescope is magic telescopes. And we are now building the 4 large size telescope in the La Palma site. And the first one is completed in 2018. And we are making commissioning and also the science and engineering run last year. And this is a Southern Hemisphere Cta South array, picture of Cta South array. Construction of the Cta South observatory will start next year. And sorry, the science of the Cta is very wide, and yeah, we can surely study cosmic ray origin, our galactic cosmic ray origin by observing supernova remnants and also the pulsar wind nebula, and also the supermassive black holes, which has a which harbor the active galactic nuclei, harbors the 10 to 8 solar mass or 10 to 9 solar mass supermassive black hole at the center of galaxy. And they are very bright with gamma rays, and we want to study also such supermassive black holes and jet phenomena from the black hole. And also the gamma ray burst is a quite interesting object, which is a burst of the black hole. And it is quite important to understand the evolution of the universe with a black hole. And additionally, we can do dark matter search by observing galactic center and also nearby dwarf spheroidal galaxy. We can see the gamma rays from the dark matter annihilation. Okay, and we are planning to build gigantic Cherenkov telescope arrays in Northern Hemisphere, La Palma, Spain, and Paranal, Chile. And we are planning to install 4 large size telescopes. It has a 23-meter diameter dish and very high resolution camera on at the focal plane. and we implemented high-tech instrument and the technology for these telescopes. And 9 MSTs, mid-sized telescopes, 12-meter size. And also in Chile, we are considering to build 14 mid-sized telescope and 37 small-sized telescope. And telescope design is shown here, I think, as a picture. LST will be built, 4 LST will be built, and 23 MST will be built, and 37 small-sized telescope will be built. But the size of their dish is different by a factor of 7 and factor of 4, and the large-sized telescope will observe mainly the low energy part of the gamma-ray spectrum from 20 GeV to 2 TeV energies. And the SST will cover higher energies, 3 TeV to 200 TeV, and the MST will cover 100 GeV to 10 TeV. And the target source is different. Source targets are different. For example, in case of LST, mainly we want to observe transient sources, AGN and the GRBs, and also the important element, dark matter at the galactic center and dwarf spheroidal galaxy. And this picture shows the sensitivity of the CTA north and south. There is a somehow focus in low energies in CTA north. Yeah, because galactic plane can be seen well in CTA south by CTA south, and we enhance the high energy acceptance and get a better sensitivity in higher energies. Okay, and these curves show the Hess magic and the Veritas sensitivity curve. So in every energy range, we have a 10 times better sensitivity than Hess and magic and Veritas. Yeah, after 50 hours of observation, we can achieve 10 times better sensitivity. And it reaches to the order of milliclav, 1 milliclav. Yeah. And also the energy coverage is very wide. We can cover from 20 GeV. This is mainly by LST, and to 200 TeV. This is mainly by SST, small size telescope. And the important thing is LST will offer the low threshold energy of 20 GeV threshold. And you can see in below 100 GeV energies, we can give the significantly better sensitivity than Fermi gamma-ray satellite. For orders of magnitude, better sensitivity can be offered. This is as a function of time, we plotted the sensitivity. So the gamma-ray burst and active galactic nuclei flare of the active galactic nuclei happens order of 1,000 seconds or the order of 1 day or a few days. So the ranging in this region, and we can offer substantially good sensitivity for high energy gammas. And this is a more wide energy range showing CTA sensitivity in wider energies. Here you can see X-ray sensitivity curves and the gamma-ray sensitivities with a satellite and a Compton telescope. And here you can see MAGIC, Hess, and the Veritas sensitivity. And the CTA improve significantly the sensitivity at the very high energy region. Yeah, especially in TeV energy scale. Yeah. And this picture shows the nice a cartoon showing the gamma-ray attenuation in the intergalactic space. We have a lot of ambient photons, not only CMB, we have light emission from stars and dust in the galaxy. And high energy gammas, TeV gamma rays, can interact with 1 electron volt visible photons from stars and make a pair of electrons. Rest mass at the center of gravity, their energy becomes 1 MeV and 1 MeV, and can produce E plus minus pairs. And this production, E plus minus production, will act as an absorption of high energy gammas. And you can see with a Z equal 0.03 source, the gammas can travel up to 10 TeV, but above 10 TeV, it drops very fast. And so on, I think Z equal 0.1, 0.25, 0.5, Z equal 1. So if we observe 1 TeV photons, for example, our range, observational range is limited with, say, 0.2 or 0.3, I think. But LST will offer 20 GeV, much lower threshold energy, and can extend the visible universe up to Z equal 4. Okay. And with a low threshold energy, we can achieve more collection of the gamma ray photons, so that we can reproduce from observation high precision light curve, for example. This is a simulation. We assume the PKS 2155 flare, which was observed by Hess. And with this template, we made a simulation, and we can precisely define the light curve with a time scale of 10 seconds or a few 10 seconds. So if something happens in time scale of 10 seconds in the black hole or in jet, we can observe it. I think we can observe it. And this is a case of gamma ray burst. We use the Fermi observed gamma ray burst, GRB 080916C. We can see in each 0.5 second time being, we see sometime thousands of photons and a few hundred of photons and a few tens of photons. And we can, it is nice, we can observe with a high precision the light curve of the gamma ray burst, and can understand the particle acceleration time scale and the cooling time from the observation. And probably it will give us some hint for the hadronic component and leptonic component in gamma ray burst. And this is another interesting topic, dark matter search. A lot of scientists is now working to look for the dark matter. And for example, Large Hadron Collider try to produce the dark matter particles, and underground detector, xenon detector, try to see the scattering of the dark matter. And our gamma ray people, CTA and also Fermi gamma ray satellite experiment can explore the dark matter annihilation channel. And here, SUSY parameter space, we can estimate the dark matter mass and interaction probability cross-section. And CTA is sensitive in this region, and LHC is sensitive below 700 GB, and CTA sensitivity becomes dominant above 700 GB. And the xenon detector will approach from the top part, higher cross-section part, and go down to this level. So these three experiments is completely complementary, and it is necessary to do such redundant search of the dark matters. And important thing is if we consider, for example, BB bar annihilation channel from the dark matter annihilation channel to BB bar, we can expect the canonical cross-section 3 times 10 to minus 26, and CTA will cut this line deeply around 1 TeV energies. We are to observe 1 TeV scale mass scale dark matter. You should have a sensitivity around 100 GB or even less than 100 GB energies. So the MST and the LST are very, very important instrument to give this sensitivity curve here in CTA. And yeah, let's talk about the commissioning status and the engineering, science engineering run with LST1. And already you have seen the nice inauguration pictures, and we made a construction of the first LST. This is a magic telescope. This is a large size telescope structure. And finally, in October or September 2018, we installed the camera and finished the construction, and inaugurated October 2018. And I hope you can see this movie well, I think. This telescope is made with a light structure, quite light, 100-ton scale. If you make this telescope structure just steel, it will become 500-ton or something. We are using the CFRP, carbon fiber reinforced plastic material for the dish structure, and making the telescope very light and enable the telescope rotation pointing within 20 seconds in any direction. Yeah, thank you. And we made 500 hours of scientific observation. It started last year, January 1st, and we reached to the 500 hours, but you can see this is not linear. It's increasing exponentially. We had really, in the beginning, we had many troubles, but the operation becomes much smoother last several months, and we are reaching really good condition in September. But oh my God, I think we had a lot of problem with COVID-19. We couldn't travel to the La Palma, and we set up the remote operation room at ICRR, and we operated telescope from the Japan, the telescope located in La Palma, okay, Spain. It is nice. At 9 o'clock in Japan, corresponds to the midnight of the Spain. So we can operate relatively good time, in good time, the telescope there. And another problem happened in September 19th. Volcano eruption started on La Palma. This is a picture of the first day of the volcano eruption. Accidentally, I was there, I think, on 17th, on 19th of September to see the new minister of the science of Spain. Yeah. However, the group of the minister canceled the travel, and I didn't know why they stopped. But after a few hours of that news, I have heard the news, the volcano erupted. And it continues longest period in history, 85 days. And this is, there is a record of the volcano eruption 8 times historically. In 600 years. So every 100 years or 50 years, we have one volcano eruption, but unfortunately, we had this eruption last year, September. And it continued 85 days until December 14th. Yeah. So we stopped the experiment and covered a delicate part of the telescope by plastic material and protected our telescope. And before that, we made a lot of observation. And now it is recovered here. Okay, this February, we sent a lot of people to La Palma and recovered the operation of the telescope. We don't see any damage from the volcano eruption. And we made a lot of engineering run. We made a lot of engineering run. This is a Crab observation. We can observe gamma rays from Crab Nebula with almost 1 Hertz, 1 event per second, 0.76 event. This is a record last year, November 20, in 21. It's a beginning of the commissioning run. So at the moment, we have almost a double of this, 1.5 times of this gamma ray rate. And Crab Nebula spectrum is reconstructed like this nicely, but we couldn't reach the targeted threshold energy of 20 GeV. This energy range is 40 or 50 GeV. And we also could measure the pulsation. Yeah, at the center of Crab Nebula, we have a Crab pulsar, and it is most famous pulsar. And we saw the pulsation, gamma ray pulsation from Crab pulsar nicely. From this P1, P2 ratio, we estimated our observing energy is around 30 GeV, 40 GeV energy scale. Okay, and this is a nice observation, nice data analysis done by Yoshiki Otani. He's our graduate student. And yeah, magic locate 100 meters from the LST, and we can make a stereo observation using the LST and the magic. And you can see background level is here and the signal is here. And we could suppress the background very low and reaching the sensitivity order of 10 milligraph. And we also carried out several active galactic nuclei observations. And Markarian 501, 421 are famous active galactic nuclei, but we also observed very distant source, one is J0647 and PG1553. This source locate 5.1 gigalight year distance. Yeah, Z equal 0.5. And this is an observation of galactic center. Even the La Palma site is a northern hemisphere. We can observe the galactic center. It's an important target, I think, for the study of dark matter. So we made a 10 hours observation with a magic, and we obtained 15 sigma XS from Sagittarius A star. But we want to see the extended component. Okay. So this is another interesting observation of the BL-like object. In August 8th, it made a really big flare. Big mean the gamma ray flux enhanced several times than Crab Nebula. Usually Crab Nebula is the brightest source in the sky, but in this day, this BL-like BL Lasseter made a flare several times higher than Crab flux at 100 GeV energies. And with this data, we made a spectral analysis and we obtained 20 GeV threshold. We confirmed LSD1 single telescope has a limited sensitivity, but it works with a low threshold energy of 20 GeV. So if we have several 2, 3, 4 large size telescope, we can surely measure this 20 GeV photons with a high precision. And you can see nice light curve, I think, in this flare. This is an intranight, 1 night, 1.8 hours observation showing the flux change, significant flux change. Okay, this is another sample of the observation. And this is nova RS Ophiuchi observation showing by LSD1. And RS Ophiuchi is a recurrent nova, and it consists of the white dwarf and red giant. And the accretion from the material of this red giant gas accreted to this white dwarf. And after the accumulation of the material, it triggered the high temperature and high density trigger the thermonuclear reaction, and it makes the explosion, I think. And every 15 or 20 years, this RS Ophiuchi make a nova explosion. And fortunately, we got this information from GCN Circular, and we made an observation, and we made a nice energy spectrum. It is preliminary. And this is this magic observation is already mentioned by Professor Kajita. It was nicely measured with a high count. It becomes 200 times brighter than Crab Nebula, which I mentioned. And magic successfully made the observation, and we found the energy spectrum. This is a low energy but XRT X-ray spectrum. Here we have a Fermi-Lat energy spectrum, and here we have a magic energy spectrum. And we can see the two-bump structure and also the light curve. This is a light curve. Magic light curve is shown like this. And the XRT light curve, magic light curve is almost parallel, evolved in parallel with the XRT. And we consider this second bump is inverse Compton component, and this part is a synchrotron component. can be explained well with synchrotron self-competent model, leptonic model, these spectrum. And on top of this, MAGIC made 3 more GRB observations. This GRB has unfortunately 3 sigma post-trial significance. This one is also 3.5. And this one, GRB observed 2020, December 16, has a 6 sigma, more than up post-trial significance is 6 sigma. This one is surely the gamma-ray burst. These are hint, we consider hint of the signal, but this one is quite interesting. This is a short gamma-ray burst, and it must be a neutron star merger. And if the gravitational wave antenna is in operation, probably we can observe together this source, I think, in gravitational wave and also gamma-ray burst in gamma rays. And this neutrino event, ICRR neutrino event, is already mentioned. Multi-messenger, beginning showing clearly the beginning of the multi-messenger astronomy. And in this direction, we Fermi-Lat observed the gammas above 100 MeV energies, and the MAGIC after this event, several days after this event happened, we observed flare, sort of flare of this source. Yeah, there is a AGN TXS 0506 in that direction, and it can be fitted well with a leptohadronic scenario. And we are now constructing the LST 2 to 4. The location, LST 1 location is here. MAGIC 1 and MAGIC 2 location is here. So these 3 telescope makes nice triangle, and we are enjoying the joint observation. And LST 2, LST 3, LST 4 will be constructed in 3 years from now on. And we can improve the LST1 sensitivity with these telescopes 1 order of magnitude. We can reach really good sensitivity, 10 times better sensitivity. And 13 countries are joining for this construction. It's 300. It consists of the collaboration consists of 300 people, scientists and engineers. And it is already a big collaboration. Entire CTA has 1,500 of people, yeah. But even LST collaboration is also quite a big collaboration. Okay, and I want to say CTA will play an important role in multi-messenger astronomy in astrophysics section, and also particle physics section, and also the astroparticle physics section, region. For example, we can observe dark matter and the neutrino together with underground detector and Large Hadron Collider, or the ice cube detector, and for gamma-ray burst and the black hole formation and the neutron star space and time problem can be studied with gravitational antenna and the radio antenna, etc. So the essentially the gamma-ray detector, high energy gamma-ray detector, will make an important role in multi-messenger astronomy. And in summary, I want to say, LST1 commissioning phase is almost completed, and we enter science and engineering operation. And we confirmed LST1 is satisfies the design performance, achieved the design performance, but adding LST2, 3, 4, we should check the sensitivity can be improved by a factor of 10, I think, by adding them. And the GRB can be observed at Z equal up to 4. And it is important we can study the GRBs in the through the star formation epoch, Z equal 1 or 2. We have plenty of the GRBs there. Yeah. And in the end, I want to mention the breaking news. This is an article shown, cited by Science, February 1st, merger of giant black holes predicted by Chinese scientists. They made a multi-wavelength observation, analyzed the multi-wavelength data for this source, SDSS J1430. And in the title, Tick, Tick, Boom, I think it is mentioned. And they observed the very interesting light curve. This is an optical band. And here you can see X-ray band observation. Here, I think very narrow. So they say this oscillation period becomes shorter and shorter in 4 period, or 5 period, 6 period. And their prediction is it is probably the merger of the 2 black holes. And now it is 100th of a parsec, or very close distance to black hole, and making the such calculation and predicting the this year, February, March, this merge can happen in some calculation, but in other calculation, it may happen in 3 years or something, 1,000 days. So thank you very much. Yeah. Hello.
Thank you very much, Professor Teshima. Now, the session is open for questions and comments. Any questions or comments, please write questions or comments in the chat in Zoom, or write in Slido in your YouTube. I will pick some up and read them aloud. Well, we have already, 2 questions. The first question is from Shumiel Yerushalmi. I will read the question.
Yes.
It is through telescopes enabling to do experiences in goal of detection, new galaxies, and witnesses of life on other planets. Well, if I interpret correctly, this question is asking you, the CTA experiment is a telescope. The telescopes aim at detection of new galaxies and witnesses of life on other planets. Professor Teshima, please.
Yeah, certainly we can observe the new galaxies. Yeah, probably which has a supermassive black hole at the center of the galaxy, and make a big flare, I think. Then we can observe it. But there is life on the other planet is a different thing. And yeah, for example, the Betelgeuse will make in 1,000 years the supernova explosion, probably. And if the rotation axis is directing to us, we will be burned by gamma-ray burst, I think.
Okay, thank you.
So the it will relate with the life, but fortunately, the axis of Betelgeuse is almost perpendicular to us, and we will not be suffered, I think, with the explosion. We can study quite detail of supernova explosion, but it is important to understand the gamma-ray burst and the supernova explosion more precisely, give us the safety of our life on Earth, I think, yeah.
Okay.
To guard ourselves, our life.
Okay.
Yes. Yeah.
And the second question from Rashmi Mukherjee, okay, about RS Ophiuchi. Was it observed or detected by LST1?
SST1? SST1?
LST1.
LST1, yes, that's right.
LST1.
That's right. We are concerned it is detected by LST1, but forget it, I think, until the publication. It's a quite preliminary.
So
yes.
the answer is yes.
Yes, yes.
Detected.
Yeah, very interesting source. And
thank you very much.
It's a new class of source. Yeah, so far there is no observation from nova. No observation of high energy gamma rays from nova. And supernova, sure, but nova is a different mechanism is working there, and a much smaller explosion. And this is the first time, I think, the observation. But I know the Hess and the Magic also observed this RS Ophiuchi signal. I don't know Veritas made a no. But 3 telescopes made an observation, I think. Or probably, I don't know the result of Hess, but they are consistent, should be consistent.
Thank you. And the third question from Carsten Roth. Observations of transient is a high priority. What will be the ratio between follow-up observations of transients at CTA versus scheduled observation programs?
Interesting question. Concerning LST, the transient is probably most important object, transient source, but the MST, and we have a different telescope, MST and the SSTs, they will make, sometimes they will also make the transient observation. However, the major stuff is a scheduled observation of galactic source and extragalactic sources. So the LST is a little bit different from other 2 telescopes.
Thank you. Are there any questions or comments? Or if not, let's thank the speaker again.
Yeah, thank you very much.
And we'll move to the next talk. The next talk is entitled Very High Energy Gamma-Ray and Multi-Messenger Astronomy, given by Professor Rashmi Mukherjee from Barnard College of Columbia University. Now, Professor Rashmi Mukherjee, please.
All right, thank you. Thank you very much. I hope you can see my slides.
Yeah.
Okay, perfect. All right. So thank you. I just want to thank everyone. Thank you to the organizers for the invitation to participate in this event. And I wish that we could have done it in person. But I appreciate the opportunity. I of course, collaborate with scientists on CTA and LST group. And I had the pleasure of visiting ICRR for the TEFPA meeting in Kashiwa in 2015, several years ago, and also working in Tokyo during my PhD years. And of course, now collaborating with CTA. So my talk is titled Very High Energy Gamma-Ray Astronomy and Multi-Messenger Astronomy. It's a pretty broad topic. And I think what I decided to do is to keep it very general, but of course, please feel free to ask me questions. I thought I'd focus mostly on the future of the field and the design drivers, the instruments under development. We just heard a very nice talk on CTA and LST, but I'd just make it a little bit broader for my talk. And then maybe I'll say a little bit about the decadal survey recommendations for VHE astronomy that was recently released in the US. And it's a process that we've gone through in the US, and it probably mostly impacts US science, but has relevance also to a worldwide collaborations. The future is, however, informed by the present. And I'd like to start out the first half of my talk just reviewing the current status of the field and some of the key findings. And we've already heard some really nice results that have been, that the field has produced. And I just sort of keep a very general overview of the findings. So just to start out with the energy ranges and definitions, as we know, much of the non-thermal universe remains to be explored. And it's important to note that two kinds of gamma-ray detectors are needed to cover this very broad spectral coverage band of 7 decades in energy, 14 decades in flux. And there are instruments both using the domain of space-based astronomy as well as ground-based astronomy. And what I'd like to do today is focus on the very high energy range, which is above 100 GeV and the domain of ground-based astronomy. So we know that there is a lot of rich potential science that's accessible to instruments looking above 100 GeV, and the range of topics is simply immense. In galactic science, we can explore sort of the winds of pulsars, accelerate particles, supernova remnants as cosmic ray accelerators. Gamma rays are produced by synchrotron inverse Compton emission. Pi-0 decays, these are tracers of parent particle population. And particles are accelerated in shocks and extragalactic jets. And the processes that we observe, these are relativistic processes and used to view the highest energy cosmic rays in the universe and outside the scope of terrestrial accelerators, really. So at the present time, due to the rapid advances in the field and astroparticle physics, we can take advantage of multiple messengers that are now available to us to study this, to study the very high energy universe. And multiple messengers, as we've heard already a couple of times today, provide complementary information. Photons, like neutrinos, are neutral messengers, and we can use this to directly probe cosmic accelerators. And gamma rays, for example, in this cartoon, you can see may be produced in an AGN jet, which may also be the source of cosmic rays and neutrinos. And in order to identify these cosmic ray accelerators, we need neutral messengers to observe, and gamma rays and neutrinos are available to us. And in fact, the search space opened up 10 years ago when IceCube announced the detection of PeV neutrinos with reconstructed energies of the order of PeV. So it's a very exciting time to be working in this field of multi-messengers. Just a little bit more detail here on what we see from these high energy gamma ray sources. If you focus on the plot on the right here, what you see here is a spectral energy distribution plotted in logarithmic scale, emission from what we measure from a blazar, an active galaxy. And these are jetted galaxies. They're the most powerful, persistent accelerators in the universe. And we measured some of these extreme blazars can have peaks in their radiated energy beyond 10 TeV. And they're really ideal targets to study particle acceleration and try to provide links to cosmic rays and also astrophysical neutrinos. And we know they exist and we measure them. We measure the spectrum. There's a lot of detailed modeling work that has gone on, which I won't get into here, but all of these, I've included the references here if you want to explore further. And then what you see in the lower plot is the nature of the diffuse high energy backgrounds that we measure. And you can see here in blue, you measure the isotropic gamma-ray background from the Fermi satellite experiment. And then in green here, you see the cosmic ray background. And right here in the middle is what's measured by IceCube and high energy neutrinos. And what's interesting here is that the energy density in all these backgrounds is very similar, and they may share a common origin. And it is not most likely what you see from IceCube to a large extent observes the same universe that we do in conventional astronomy. So there's a lot of interesting overlap between all these different multiple messengers. Let's just focusing on the gamma ray instruments for a moment. Just if you look at the synergies, this shows the interconnections and where the opportunity to basically have a synergistic and combine complementary strengths for these space and ground-based instruments. And if you look at the IACTs, the imaging atmospheric Cherenkov telescopes, the current generations, the HESS, MAGIC, and Veritas, these sort of sit perfectly wedged between the satellite experiments, which cover a lower energy range, and the wide field of view experiments such as HAWK, Tibet, and others, and Lhasa now, which really, I'm going to cover Lhasa more in the future prospects of the field. But really, these are complementary strengths, and what you gain in sensitivity with these imaging telescopes, they lose out in field of view, and of course they can only observe at night, but they have really exceptional sensitivity despite the limited field of view, and would be great for transients. But on the other hand, the large field of view experiments such as HAWK, for example, these have high duty cycles and great for studying extended sources. So the complementarity of these and the fact that they are operating at the same time have really added to the wealth of the knowledge in this field. This, I think, I don't need to introduce the detection techniques to this audience. I think you're all experts here. But the one point I'd like to make here is that for very high energy studies, this really shows the complementarity and the fact that while for an imaging telescope, atmospheric Cherenkov telescope, which can use stereoscopic techniques, you really have a very large collection area. But on the other hand, when you're looking at this 100% duty cycle, large steradian field of views, large collection area, they're looking at the primary particles directly, either using water Cherenkov or particle detectors. So nobody's really shown this so far, so I'm just going to quickly flash this. These are the three major imaging atmospheric Cherenkov telescopes currently in operation for the last 10 years, in fact. You can see Veritas is located in Arizona, 4 telescopes. MAGIC in the Canary Islands, as we just heard, these are the 2 17-meter diameter telescopes, low energy threshold, and really great in looking at active galaxies, gamma-ray bursts now, and the low energy threshold really helps it. And then in HESS, at the HESS instrument in Namibia, which added a very large 28-meter diameter telescope, so it's actually a hybrid array in some sense, also providing access to lower energy threshold. And then to complement that are the water Cherenkov experiments. And here you see an image of the HAWK experiment, a photo actually at the Sierra Negra Mountains in Mexico, 4,000 kilometers above sea level, and very large field of view, 100 GeV to 100 TeV. And then I will mention Lhasa later on in the talk. But this is basically, these are the instruments that have been working now for 10 years and produced spectacular results. And what you see here is a summary plot which shows all of the very high energy sources detected, more than 250 sources now at TeV energies. And this is now overlaid on the Fermi-LAT large area telescope results. And you can see actually what's interesting here is that this is the diffuse emission from Fermi. You don't see the point sources, but you do see the very strong galactic diffuse emission. And it's interesting that the TeV, or the very high energy sources overlaid on this, several of them are unidentified and could be pulsar wind nebulae, but this is something that we are exploring. But the point here is that the imaging telescopes have demonstrated their successful technique, and precision astronomy is now possible with detailed measurements of spectra and light curves. And we've gone beyond discovering sources, just one or two sources. And now it's possible to do even things like population studies, measuring sky maps to 5 arcminic resolution, light curves that are timescales of minutes to years, and very detailed studies, including, I think what's really interesting in this plot is, and I think somebody mentioned this earlier, that it's not just the number of sources, it's the different classes of sources. Almost every source that you see in the universe is a gamma-ray, high energy gamma-ray source. So this is all very exciting for the field. And what I'll do next is just show you a couple of results, just a couple of highlight results from these, the current generation instruments, just to highlight their strengths. And here, for example, is an image, is a sky map of the sensitive surveys of the galactic plane. And this was first carried out by HESS, the instrument in the south in Namibia. And this was one of the deepest and most comprehensive high resolution, down to 0.1 degree sensitivity, and sensitivity to less than 2% of the Crab Nebula, which is the standard candle for TV astronomy. And this was down to about 2% of the Crab Nebula survey of the Milky Way. Large number of sources were detected, several were unidentified. And we are learning now more with results now from HAWK and from LASSO as well. And what was interesting is that HAWK was also able to, the water Cherenkov detector, able to carry out a sensitive survey of the galactic plane. HAWK has in fact reported recently the detection of 100 TV gamma rays coming from the Cygnus cocoon super bubble that's located in the region of star formation region in the galaxy. And what was interesting in this particular plot is an analysis of the HESS galactic plane data, applying an analysis technique that was able to more easily compare the results that HESS and HAWK both detected. And these are basically events above a TV selected from both data sets, with the point spread function of HESS was broadened to approach that of HAWK. And what you can see is that the results are very consistent from both these instruments. So a little bit more detail on individual sources. This is a spectacular measurement of a supernova remnant. This is what's possible now with imaging atmospheric Cherenkov telescopes. We're able to resolve the morphology of some of these sources. What you see here on the left is an image of RxJ 1713 minus 3946. It's a supernova remnant where it was possible to really image it and spatially resolve it, and also compare it to other wavelengths. And in this case, the blue contours here show you the X-ray contours with XMM, and you can see that there are the match between the TV and the XMM is quite great, and in the highlights, and they match quite well. And it was possible to do things like correlation of X-rays and TV studies, and there's a lot of detail here. The source has been studied quite extensively. But one of the interesting things that they found is that there is correlation between the X-ray morphology and the TV morphology. And in fact, you could even carry out spectral studies in different parts of the remnant and compare the radial profile of the X-rays and the gamma rays. And on the right, you see another example of northern supernova remnant, IC443, that was also resolved by Veritas. And there was a close match that was found between GeV and TeV morphology and distribution of shocked gas. So there's a lot of work again that's going on in these new sources that have been detected by HAWK. So these are gamma ray halos. It was reported, I think, in 2017, the detection of extended TeV gamma ray emission that was coincident with locations of a nearby middle-age pulsar. And you can see here's this HAWK sky map. Here's the Geminga pulsar, and there's another pulsar here. This is all inside the monogem ring. And this was reported. What was interesting is these observations demonstrated that these pulsars, what HAWK reported was that they are indeed local sources of accelerated leptons, and the emission profile can be used to constrain the diffusion of particles from these sources. And you can see here the emission profile for these two sources, Geminga and the pulsar. So I think moving away from so these are all galactic sources, and just moving away to extragalactic sources. And Professor Teshima mentioned this in his talk, so maybe I won't spend too much time on it, but I think the extragalactic gamma ray sources are blazars. These constitute the largest source class for TeV instruments. for the imaging atmospheric Cherenkov telescopes. And this cartoon here summarizes the physical processes. And active galaxies, these are powered by accretion onto a supermassive black hole, can be 10 to the 6 to 10 to the 9 solar masses. And what you see here is what we see for the Cherenkov telescopes is we're able to measure ultra short timescale variability down to minutes timescales. These sources have extremely hard spectra, and the jet power can be extremely high. The isotropic luminosity can be 10 to the 48 ergs per second, and we need GeV, TeV particles, are needed to make these gamma rays. Basically, if you're seeing gamma rays, you need to be able to accelerate them to GeV and TeV energies. This is a plot that demonstrates some of the unique capabilities, and the short timescale variability is one that I'd mentioned. Here is a measurement of a particular flare from an object. It's called BLAC, where the emission was resolved to a few minute timescale bins, and one could measure the timescale, a rise time and a short fall time of the order of a few minutes. And this actually helps to constrain the size of the emission region, which was constrained to a few Schwarzschild radii. And in this particular case, there was an interesting observation with VLBA, the Very Large Baseline Array, and measurements at 43 gigahertz at the time of the TeV flare also measured the ejection of superluminal radionauts. And so this is a question that is actually an open question is being studied, is what is the relationship between radionauts and gamma ray flares? And there's some collaboration that's going on along these lines. And this is, of course, the famous plot of PKS 2155 minus 304, where the black dots are the actual measurements carried out by Hess, where the burst in emission was 15 times the Crab Nebula flux, doubling times of a few minutes. So in the world of, I think that one of the most exciting results in the last 5 years, this is in the field of multi-messengers, is the association of a high energy neutrino with a flaring blazar. And we've heard about this already a couple of times in this workshop today, but this was the first evidence of a multi-messenger association of a blazar flare with neutrinos. And when IceCube announced this was in September of 2017, the neutrino emission was 290 TeV, and there was a flaring blazar. Fermi-Lat reported, which led to an extensive multi-wavelength campaign. The source was detected by MAGIC, and you can see here the MAGIC image showing you the location of the center of the MAGIC emission, the Fermi position, and also the 50 and 90% confidence contours of the IceCube emission. And this is one of the motivations and one of the goals for the future, also for CTAs, to find other neutrino associations with blazars. The other big multi-messenger goal, of course, is a top priority for imaging telescopes is to follow up on Ligo and Virgo gravitational waves. And these, as you know, may be generated in cataclysmic collisions of merging neutron stars and generation of gravitational waves and GRB events. The most famous one, of course, was the first one was 170817. This was detected by Ligo and Virgo, and there was a gamma ray burst emission that was associated with it, electromagnetic observation of multiple wave bands. There was no detection by Fermi Large Area Telescope, and there was no report of any detection by ISCT. So this continues to be a top priority for the imaging telescopes. And recently, actually, this was the exciting news that gamma ray bursts are indeed VHE sources, and in fact have been detected by both MAGIC and Hess. And I would say after this was one of the highest priority science topics for the imaging telescopes. And after more than a 15-year search, several GRBs have been now reported having been detected by both Hess and MAGIC. And I'm not going to go through the list of these sources, but the point here is that both long and short GRBs were detected over a range of redshifts. The long GRBs are detected during the afterglow phase, and this could be the tip of the iceberg and certainly motivations for future observations. And then I think we just heard this is a new TeV source class. This was very exciting. And I think the point here is that there is always room for discovery for the ISCTs. And we've demonstrated that even after 15 years of operation, as recently as last August, there was an exciting report of the detection, and there was I think there was a telegram by Hess on the detection, 6 sigma detection of gamma-ray TeV emission, and we just heard from LST1 as well of the TeV detection from this RSOFU-K, which is a very interesting system. It's a high mass white dwarf red giant binary system, and of course it was also detected by Fermi Lat. Nova R have been detected by Fermi, but never by TeV instruments. So this is a brand new source class and a very exciting one indeed. So I think I'm just going to stop with this last slide here for the current results. I won't get into too much detail here, but one question is, what is the gamma ray horizon and how far out can we see? And what you see here is that both Hess, MAGIC, and Veritas have reported the detection of active galaxies out to a redshift of 1. Not beyond that, and that is the low energy threshold is what is needed. And I think that's one of the motivations for getting to a lower energy threshold also with future instruments. And this is a very important topic for cosmology, and also in here, actually, there are 2 examples that I'm giving you. PKS 1441 plus 25, it was an unexpected discovery of this quasar by MAGIC and Veritas. And for this one particular source, even a good spectral measurement could give you an idea of the extragalactic background light to understand more about this source. So there's a lot of, which I'm skipping, and it's a pity, but I think that I want to move on to a little bit more and spend a little time on the future of the field. That's where we are heading, and that's there's opportunities for collaboration there, and the future looks really exciting. And in the next decade, there's several experiments are planned and are already operational, as we know from both LHAASO and CTA. And I'll just quickly mention 3 of these. One is LHAASO, the other is the Southern Whitefield Gamma Ray Observatory, and then the last one is CTA, the Cherenkov Telescope Array. And maybe at this point, I'll just take a minute and just talk a little about the Astro 2020 and the next decade. So in the US, there's been this exercise that we got a little delayed because of COVID-19, but we have been anticipating with interest the Astro 2020 Decadal Survey and what it says about VHE astronomy. And as we know, the goal of Astro 2020 was to describe a pathway for the next decade and for major scientific breakthroughs and discoveries, and also to identify the high priority science and timely science that we want to do, keeping in mind the US participations. And this is actually a slide that I took from a recent town hall meeting, NSF town hall meeting, and was a slide that was presented by the NSF Astronomy Division Director. And what basically what she's saying here is that the Astro 2020 identified 3 kind of big pillars, 3 main pillars of science themes. One is exoplanets and habitable worlds. The other is time domain multi-messenger astrophysics, and the third one is the CMB, cosmology and evolutions of stars and galaxies. And for us in the field of VHE and multi-messenger is the second pillar here on time domain multi-messenger that is particularly relevant for us. And I think we're very much working in that direction, both in the US as well as in the world. And just I'll start with LHAASO as the first sort of the next generation instrument that is already operating. It's in China, Sichuan, China. And it has reported, if you were at the ICRC last year, you probably saw that they've reported spectacular results already. It's a combination of detectors. It provides a broad spectral coverage, high duty cycle, and there's a lot of work that's happening. The great thing is it can see a large part of the sky all at once and has 100% duty cycle. LHAASO has already produced first results, and what you see here is a sky map above 100 TeV. These water Cherenkov detectors are actually really proving to be Pevatron hunters. Pevatrons, as we know, are believed to be the highest energy sources of cosmic rays in our galaxy, and their definitive identification has been elusive so far. And these can accelerate protons to PeV or peta-electron volts. And you can see here that this is a sky map that shows a large number of gamma rays above 100 TeV. And this plot here is a spectrum of the Crab Nebula, which is an extraordinary accelerator And you can see it's a combination of measurements from several instruments, and the highest data points are from Lhasa, and deducing from that, you can conclude that the Crab is in fact a confirmed extreme accelerator, 2.3 PeV electrons. The other big thing that's happening, I mean, based on basically knowing what we know from Hawk and now with LASSO, there is really a strong motivation for a wide field southern Gamma-Ray Observatory in the Southern Hemisphere, complementing LASSO and providing a complete view of the TeV and PeV sky. And this is work happening now, the strong synergies also with CTA, as well as multi-messenger and neutrino experiments. And there's, again, there's, I think at this stage, they're looking at the site and exploring concepts and thinking of the science that can be done. And then finally, there's the Cherenkov telescope array, which, as we know, will be the world's largest, most sensitive gamma-ray instrument observatory. It'll consist of different kinds of telescopes, as we just heard. It's a large collaboration, more than 1,500, about 1,500 members, I think, about 25 countries, of which it's already part of the large size telescope is already, the prototype is already working really spectacularly. Very quickly, the design drivers for CTA, just again, based on our experience with these imaging atmospheric Cherenkov telescopes, the goal is, and this is a simulated sky with what we might see depending on where we look, different kinds of sources, but the goal is to have a sensitivity which would be a factor of 10, a full sky coverage, arc-minute angular resolution, and then the ability to slew rapidly for transient follow-ups, and also cover a very broad energy range. And the idea is that you do this by using a combination of telescopes, again, using a combination of technologies, telescopes, each of which is specialized to a particular kind of science and overlap with the overall scientific mission of CTA. And what you see here, and I'll talk a little bit more about this, shaded out in gray, is the dual mirror Schwarzschild-Curie telescope. And this is something that we are working on in the US, and also myself personally. And the reason it's shaded out is not part of the current status of CTA is to build the project in phases. And in the early part, the alpha phase of the CTA observatory operation in the alpha configuration will consist of these sites, northern and southern, north in La Palma and south in Chile. And the initial construction, in the initial part of the construction, there will be a certain number of telescopes, and which I won't get into the details of the numbers, etc. But there is the goal that in the US that the Schwarzschild-Curie telescope would be included in the enhancement phase, which is beyond the original alpha configuration phases. So CTA is already operating, as we heard. The LST has I mean, my slide is a little old, and you heard from Professor Teshima that this is already working. And I think one of the spectacular things is the beautiful measurement of the Crab pulsar, which already was detected by MAGIC and Veritas, and was a surprise actually to see the pulsed emission. But now we see this also from LST1, and as well as several active galaxies. And then maybe what I'm going to do now is just focus a little on the Schwarzschild-Curie telescope, which is what we are building in the US. And the idea here is the goal is to build this in the enhancement phase of CTA, is this dual mirror telescope, which, because of the way of the geometry and the optics and it would have really superior angular resolution over a wide field of view, 8 degrees field of view. And by focusing light on a smaller surface, this actually enables the use of state-of-the-art sensors and technology and better sensitivity, better points per resolution. So where are we with the SCT? What you see here is actually an inauguration picture. This was in January of 2019. And I think it was around this time that the first gamma-ray burst ever was announced, the detection by MAGIC, which was really an exciting time to be having this inauguration and looking already in the future. This is now partially built. It's in Arizona. We've announced the detection of the Crab Nebula. In October 2020, the CTA consortium endorsed the development and construction of SCTs for the enhancement phase. And right now we are actually upgrading this and building a larger camera for a full 8 degree field of view. And this is actually has been endorsed by the Decadal Survey as a contribution and as an essential element for US multi-messenger strategy. So just a couple of slides and I'm just finishing up here. So what did the ASTRO 2020 say about CTA and the Southern Wide Field Gamma-Ray Observatory? There was a panel of particle astrophysics and gravity that recommended participation in both CTA as well as Southern Wide Field Gamma-Ray Observatory. CTA was recognized as a mature project ready to move forward. And I think that I won't get into the details of the construction and cost, et cetera, which of course was subject to change. But let me just sort of end here with showing the ASTRO 2020 Decadal Survey endorsements for the continuity of multi-messenger capabilities. So this is a high level sort of a schematic view of the different messengers over the decades. In the future, what you see here is both existing as well as planned projects, and then also missing opportunities, which ASTRO 2020 has encouraged to explore. But with each messenger, the discovery prospects are really outstanding. And with multi-messenger observations, these could be transformative. So let me, since I'm out of time, let me just sort of end here and summary and outlook. So CTA is going to really cover the broad energy range, 20 to 300 GeV. We will work in collaboration with LASSO, which is already giving us unprecedented results. And in the future, hopefully with the Southern Wide Field Gamma-Ray Observatory. And together, I think this is really an opportune moment. And the one thing that I'd also like to mention is that the one thing that's missing right now is a satellite mission in the MEV and GeV range to complement this sort of high energy part of the spectrum, which right now doesn't exist and hopefully might happen in the future. So let me just end here and thank you for your attention and let me answer any questions that you might have.
In Zoom or write in slide 2 in YouTube. I will pick some up and read them aloud. Or any questions or comments? Oh, or if no, let's take a lunch break. So thank you, Rashmi, for your excellent talk. So thank you very much.
Thank you.
Well, lunch break, and we arrange a poster session during the lunch break. If you are interested, please join the poster session. The next oral session will start at 13:30 as is scheduled. See you at the next session. Bye-bye, see you. Good afternoon, everybody. The first afternoon session starts now. The first talk is entitled Highest Energy Cosmic Ray Observatory in Utah Telescope Array, given by Professor Hiroyuki Sagawa from ICRR. Professor Hiroyuki Sagawa, please now.
Thank you very much. Okay.
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 Okay. I can see your slide.
Okay. I talk about the recent result from the telescope array. This is the outline of my talk. Actually, there are many TA results, but today I talk about the highlighted subjects. Cosmic rays were discovered in 1912. They are high-energy elementary particles from the universe. Main components are protons, others nuclei, and electrons. They arrive to the Earth very uniformly, 0.1% level anisotropy. The origin is a mystery. How powerful are ultra-high energy cosmic rays? Cosmic ray energy range from 10 to 9 electron volts to 10 to 20 electron volts, which is very much powerful than the human-made accelerator. Cosmic ray flux decreases very rapidly as energy increases. At 10 to 20 electron volts, the arrival rate is less than 1 event per 100 square kilometers per year. So the huge detector is necessary. Oh, sorry. So 100 square kilometers, how large it is. So left is New York, and right is Tokyo. Scale the area is 100 square kilometers. So what are candidates? Active galactic nuclei, the most powerful massive black holes and jets, and cluster of galaxies, the largest gravitationally bounded objects, and the new magnetars with the strongest magnetic field, and gamma-ray burst, that is the most violent explosion. So how can we explore the origin of ultra-high energy cosmic rays? So since there is a magnetic field in the universe, such as the magnetic field of the our galaxy and extragalactic magnetic field outside of it. So cosmic rays are charged particles, and low energy cosmic ray bend by the universe magnetic field. So the arrival directions are almost isotropic at the Earth. But the highest energy cosmic rays travel almost linearly against the magnetic field. So we can trace back the arrival directions, and we may find the source of the highest energy cosmic rays. So what happens when the ultra high energy cosmic rays enter the Earth? So the primary cosmic ray collide with the nucleus up in the atmosphere, and many particles are generated. So these collision processes are repeated in cascade ways, and which can grow to billions of particles. We call it air shower, extensive air shower. So how do we detect the ultra high energy cosmic ray air showers? When a primary particle enters, many secondary particles are generated, and the fluorescence light is generated, and they are detected using photomultiplier tubes with reflecting mirrors. We call this system fluorescence detectors, or FD. In addition, there are particle detectors on the ground. We call surface detectors or STs, which directly observe the penetrating particles. And there are two largest, highest energy cosmic ray observatories. One is the TA in the northern hemisphere, and the other is PROJ Observatory in the southern hemisphere. The TA detector is located in Utah at 39° north latitude, 1,400 meters above sea level. We deployed 507 surface detectors, each with 3 square meter scintillator on a square grid of 1.2 kilometer spacing. Totally, they cover approximately 700 square kilometers. We built 3 FD stations. They see above SD array. Hybrid observation started in 2008. The observation of FD is performed at moonless night with clear sky. The duty cycle is about 10%. And these are mirror. These are mirrors, these are cameras. Light from the light from an air shower coming to the FD is reflected with mirrors, and the photomultiplier tube is in the camera and detect the light.
Just a moment. 共有。共有。なんかおかしくなったらな、その。共有。
This is light, US light pollution map. You can see the east side and the west coast are very bright. And Utah is here, and it is nice and dark. And here is the TA. So this is a scintillator detector. And when the secondary particle enters, scintillation light is emitted, and through the optical fiber, light is transferred to two photomultipliers. One is the upper layer, and the other is the lower layer. And the signal is digitized in the electronics at the SD. And here we can see a surface detector deployed on the desert. And we can see another SD here, and here, and here, possibly one more. And there are batteries and electronics under the beneath of the solar panel, and the duty cycle is 100%. And TA observed the event down to around 10 to 18 electron volt, and to lower the energy, we have TA low energy extension tail, and the aim is especially for the study of the transition from galactic cosmic rays to extragalactic cosmic rays. And there is a tail FD, and FD observed elevation larger than TA, and there is the tail SD with a smaller spacing than the TA. They are located at the northern side of TA. And we have highest energy extension, TA times 4. The goal is to quadruple the TA-SD array, adding 500 SDs with wider spacing. And that is aimed for the data collection speed up for the highest energy cosmic rays. And so far, 257 deployed as shown in red, and we have 2 FD stations here and here. And this slide shows how we have constructed T times 4 surface detector. We assembled detectors in Japan, and number 2 at the Cosmic Center in Delta City. Anyway, we shipped detectors from Japan to the United States. And number 3 is a view, of full SDs in the east lot of the Cosmic Ray Center. And number 4 is Japanese researcher Kido-san is traveling in the desert with buggy for staking. That process determined the SD position to be deployed. Okay, one by one, like this. And they were, the SD is transported above the desert by this helicopter. So the So this is a list of the collaboration of the TA, and there are 160 members of 36 institutes from 7 countries. And let's move to the TA result. First, the energy spectrum. So this is what an event looks like. The footprints of the air shower with ST on the ground are like this. And horizontal axis shows the west to east, and this is from south to north. And the size of the color is signal size, and color, the size of the circle is signal size, and the color is time. The direction is determined by the time fit, and the direction is here. And we determine the energy from the lateral distribution, and we use this S800 particle density at the 800 meter from the shower core. And this slide shows the shower reconstruction. And shower reconstruction with FB. Can skip this one? Okay, so I show the energy spectrum. The left figure shows the TA ST energy spectrum. And since the energy spectrum decreases, flux decreases very rapidly, vertical axis is the flux multiply the cube of energy. And we see angle here and the cutoff here. And we also show the TA times OST energy spectrum, and it is consistent with the TA ST energy spectrum. And this cutoff, originally the DGK cutoff was, this process was proposed by these 3 persons, and this means cosmic ray proton with 10 to 20 electron volt coming beyond 50 megaparsec cannot arrive at the Earth by the energy loss due to the resonant interaction with the CMB. So in this case, this source is limited within a certain distance, the ZK horizon, and also ultra high energy neutrino and ultra high energy gamma should be observed. And this is energy spectrum TA, ST, and TA low energy FD. We see these five break features, and we also see the in-step structure. Originally, it was reported by OJ, and around the highest energy, we have some shoulder here, and TA, SD, and FD, and high-res data are used, and this combined fit also shows the in-step feature, and this significance is 5.3 sigma significance. Okay, next composition. So what particles are UHCR cosmic rays? So this longitudinal shower development is observed with the FD, and this longitudinal development depends on the shower primary particle type, and we use X max, which is shower maximum depth, and this depends on the maximum position, depends on the shower particle type. And this is a result of the TA hybrid composition, and this is an X max at the certain this energy bin, and black is theta, and red is proton, this is helium, and orange is nitrogen, and ion in blue. So TA data is consistent with light composition like proton or helium. So this figure shows elongation rate, average X max versus energy, and so it is consistent with the light composition. And this is a TAFD monocular X max, and this is a average X max versus energy, and we see a break here at 10 to 17.2 electron volt, and this position is found as a second knee in the energy spectrum, so it's very interesting. And also this is a comparison with models. These are TA data, and proton and to ion compared, and so from first knee to second knee, the composition becoming heavier. And also we searched for the ultra high energy photon limit, and so the profile some features are different between proton and gamma, and using proton gamma classifier based on neural network using composition sensitive observables from time resolved SP signals, and we extract one parameter xi, and we can see the tendency to the proton Monte Carlo and photon Monte Carlo shows a different behavior, and in excess, so we obtain the upper limit like this, and this is an comparison with the DZK model. Okay, next anisotropy. So this is an arrival direction of the TA, highest energy cosmic ray, above 57 eV, and these are the these points are the arrival directions in the equatorial coordinates, right ascension and declinations, and this is a celestial equator, and above this line is a TA field of view. We have 72 TA events, and using oversample circle of 20 degree radius, we show some significance map, and the highest significance was obtained to this direction, and within the 20 degree radius circle, 19 events were observed, and so the 4.5 expectation. And the post-trial significance was 3.4 sigma. We call it the TA hotspot, and this is close to a super galactic plane. And we updated the hotspot, and total event is 179 above 57 EV. Using 25-degree oversampling, we obtained this significance map, and maximum was obtained to this direction, and chance probability obtaining this was 3.2 sigma, and this is an anisotropy at a bit lower energies. This case above 40 MeV, 40 eV, and we see some excess at a different direction, and this is a direction to the Perseus Fishes supercluster, and chance that the excess within 90 degrees of a supercluster center was 3.5 sigma. And this is a significant map together with TA and OJ, whole sky analysis, and TA hotspot here, and other excesses here. And these are close to so-called starburst galaxies. And this is an famous M82, and also a hotspot is close to Ursa Major Center. And also this red and yellow that shows some excess is close on the supergalactic plane. And we also observe the declination dependence of the spectrum, and this comes from the originally the TA-OJ spectrum difference at the highest energy, and in the TA-OJ common band, declination common band, and actually we had the same cutoff energy. TA case is this one, and although the OJ data is not shown here, but consistent cutoff is obtained around here. And for the higher declination area of the TA, the cutoff position is here. The difference of these two different declination area, the cutoff difference is like this, and this difference is 4.3 sigma. So it's very interesting. And just before the conclusion, highest energy event by surface detector was observed by TA last year, and this is 244 EV, and this is the highest with the surface detector measurement. Okay, that's a summary. Okay, thank you very much.
Thank you very much. Sorry for the network trouble, and thank you for the speaker. And any questions or comments? Please write questions or comments in the chat in Zoom, or write in Slido in YouTube. I will pick some up and read them aloud. Any questions or comments? If not, it's the schedule is tight. So let's thank the speaker again. We will move to the next talk. The next talk is entitled Zeroing on the Sources of Ultra-High Energy Cosmic Rays and Very High Energy Neutrinos, given by Professor Glennis Farrar from New York University. Now, Professor Glennis Farrar, please.
Can you see my slides? Did I successfully share the screen?
Clearly, but not presentation. It's not.
Oh, huh. It's not presentation mode. Is it, what are you seeing? Are you seeing?
Yeah. The first page.
Oh, okay. So it's okay.
Picture.
Does it seem okay?
Not full screen yet.
Oh,
I guess.
huh.
Not full screen yet, I guess.
Sorry. This is mysterious.
Mysterious.
I'll do a new share.
Now I can see you.
And I especially wanted to thank Sagawa-san for that really great overview of cosmic rays, which lets me.
Yeah, great. Now it's okay.
Okay, sorry. And I thank you everyone in Tokyo for still being up or being up again after a nap to hear this talk. It's really a pleasure to be able to see you, Amelie. I really wish we were seeing each other in person in New York. So the topic I'm going to tackle is to try to explain that in spite of the problem being very, very challenging, I believe there's a very clear path forward, and we already know a great deal about the origins of cosmic rays and the highest energy neutrinos. I put in this picture of the samurai because I think it takes a great deal of courage and endurance and skill to be able to do this work, but I'm sure we're up to it. I'll describe briefly what the challenges are, but then try to explain where we stand now, which is much further along than I think many people appreciate it. One of the things I want to start by stressing is there's a great complementarity between the uncharged multi-messengers and cosmic rays. First of all, the fact of the GZK horizon is a huge help when you're attempting to make source identifications because you're not seeing the whole universe. With neutrinos, you have an Olbers paradox problem, effectively. That is to say, there's so many different sources out there in every direction. With photons, they also have a limited, gamma rays, they have a limited horizon, of course. The other thing is, there's this time delay from the propagation in the extragalactic magnetic field, which will delay the arrival of the cosmic rays relative to the photons or neutrinos or gravitational waves from some source by tens of thousands of years typically. So that means that the strategy of time correlations that can be used, for example, between a gamma ray, a high energy gamma ray and a neutrino to argue for a common source to reduce this background problem is not available for ultra energy cosmic rays. But it has a flip side. There's a very, very, very positive flip side that, as far as I know, no one ever commented on before. Namely, that time delay means that we're integrating the signal over tens of thousands of years. That means that when an observatory, let's say TA's hotspot, that might have been produced by a transient that happened 10,000 years ago. Of course, a transient, and it might be a very rare new class of transients that are so rare we don't see them in the optical, or certainly not with neutrinos. Anyway, I just wanted to make that comment that there's a flip side to this issue of the time delay. The other comment I wanted to stress is that, well, ultimately it's the whatever it is that makes ultra high energy cosmic rays this perhaps the most interesting thing. How is it conceivably possible to accelerate particles to such high energies, and what are the sources like? A key to figuring that out is going to be the composition and spectrum of the cosmic rays themselves. Just identifying, let's say we could identify very well by neutral particle astrophysics, some class of possible sources. That won't tell us how they work. All right, so that was just to sort of, let's see if I can progress this thing. So I will now launch in. And so what we know is there's no apparent dominant source. There may not even be a dominant source class. We know the composition is complex. The cosmic rays at the very highest energy of the galaxy overlap with extragalactic cosmic rays. There's a transition region between the two. I'm going to talk about is how the propagation and interactions in the environment immediately surrounding the accelerator shape the spectrum and leave an indelible imprint, which I'm going to argue is very key to being able to identify what the sources are. Let's see that. So what we need to know, well, we want to know a basic thing is, are the sources weak and abundant or strong and rare? For years before the field developed, it was assumed they were strong and rare because the energies are so exceptional. How could you possibly make such high energies except with some really remarkably rare source? But that's somewhat, that argument is defeated if, as Auger has found, the cosmic ray composition is heavy so that the charges are high, so that the arrival directions can be smeared out. In that case, you might still have a few very high energy, very rare and powerful sources, but when you look at them, they're sort of spread everywhere. However, I'm going to argue to you that there's an analysis that indicates pretty strongly that, in fact, the sources are fairly weak and abundant. I think I will just move along. Okay, so there's challenges and opportunities, as I'm arguing. Composition is an essential, but I want to say just a technical challenge. We need better particle physics to describe the evolution of air showers, so there's not any uncertainty from that, and we need better detectors. That will come. The magnetic deflections are also a challenge, but I'm going to argue that actually it's all converging quite well. So in this talk, I'm going to give a brief overview of the magnetic fields issues. I'm going to talk about the Auger dipole anisotropy and what we learned from that. I'm going to claim that that gives us a baseline model. It's a model that fits the data beautifully, and any other model would have to be taken in that context. It demonstrates that the sources are abundant and weak. That means, TA people should perk up their ears, that means that individually evident sources are rare and few because they have to be very close to stand out against the background. And I believe that the TA hotspot is very likely to be one of those. The Auger hotspot, on the other hand, can be completely described by this continuum model. We'll wait and see how that comes out. It depends a lot on the composition. And then the last part of my talk is to describe work done with my student Marco Muzio, in which we use information in the spectrum, detailed information in the spectrum and composition of cosmic rays and the spectrum of neutrinos to zero in on the source type. All right, so let me quickly mention the galactic magnetic field. The standard field that people use is the one, only because it hasn't been significantly improved on in the meantime, that my student Ronnie Jansen and I fit to for the first time. That's why it was a powerful step forward. Not only using Faraday rotation measures from extragalactic sources, that's the data shown here, but also for the first time polarized synchrotron emission from we used WMAP. Now it's improved. Planck has better emission data. Anyway, these 3 sets of data constrain to a quite a good degree what the field model is. This is an illustration. If you had a colloidal field, by the way, it's a directed colloidal field. That was really unexpected. Then if just the differential rotation of the galaxy twists it up, and then it has that form. So this is what we actually have. The making further progress, lots of people are trying. I've been working on it for a long time, but it's very interconnected because you have to know the cosmic ray electrons, which in fact depend on the field. You have to know the thermal electrons, which also depend on the field, and so on and so on. So the reason it's been hard to go beyond what Ronnie and I models on the shelf is to actually now one should improve all of those things at the same time. Nonetheless, the point I wanted to make is that for our purposes, it's certainly a good first approximation. I'm sure it's not right in detail, but it can give us a good idea of what to expect. So this is some key examples of what a source at different positions in the sky would look like. I picked out M82 and Perseus because of TA. Under here, M82 is hidden. Here you can see it. And what you see is that if it was all protons, you could go down to 10 EeV without getting a huge amount of dispersion from the source. It's still significant. It's maybe 10 degrees. But as soon as you go down to a significantly lower rigidity is what counts, of course. It's the energy divided by the charge. To be looking at this plot, if it's helium, it has to be 63 EeV. If it's carbon, you need it. You'd be looking at this plot if the carbon has 63 EeV. Excuse me, I miswrote that. That should be EeV. And so what you see is, I believe the takeaway is that it will be super valuable to be able to tag the composition of individual cosmic rays, because then you know to just put aside the ones that have a high charge and concentrate on the low charge ones, and then you can map out your source better. So this shows Perseus and how it develops. It's, in fact, even at the highest energies, there's a substantial deflection there, and so on. This is the Cta. It's a similar story. An important thing to comment is that the actual smearing from extragalactic deflections is basically negligible. It's maybe a degree or something. But the extragalactic deflections have a very major impact on the arrival time because the distances of the sources are so huge. Actually, this is a virtue in two ways. One comment I was making is that it lets you integrate over time in getting to see transient sources. And the other thing is it gives a very distinct imprint, a signature for a transient source, because a transient source, I forgot to put in a plot, has a very peaked spectrum, because what happens is the highest peaked in rigidity spectrum is because the events that have high rigidity have already passed, so that part of the spectrum is depleted, and the events which have low rigidity haven't yet arrived, because those take longer, more diffuse paths. Therefore, by looking at the spectrum as a function of rigidity, you can definitively decide whether your, let's say, TA hotspot is a transient or not. It's hard, a little bit hard for things to not be transients, frankly, because, again, of the power and the energies involved. All right, well, I think, and I want to just emphasize, this is a picture of the Auger prime, one of the detectors. Auger originally just had water tanks and then the fluorescence, whereas TA has, as you saw, the scintillators and fluorescence. Now with Auger prime, the Auger tanks are getting their own scintillators too. And when you have scintillators and water tanks, it's fantastic because you separate the electronic and the hadronic signals. A very important and I think exciting development within Auger is using artificial intelligence to study the signals on the ground, and the progress is remarkable, actually much more exciting even than I had hoped. It seems to me there's a good chance, and I'd love to discuss this with the TA people, maybe afterwards or if there's a break or we can Zoom later. It seems to me that to the extent that, of course, right, Auger may, through this combined detector and the AI, be able to come up with a very useful AI diagnostic using just the TASD, the surface detectors, the scintillators, in order to discriminate charge. All right, so this is now, this is a baseline model. The idea is, supposing sources were very weak, then they would follow the matter distribution of the universe. We learned the matter distribution from the universe from the cosmologists. This is the picture of the best current version. We know that how their propagation affects their, that causes light particles to disintegrate and so on and so on. The effect is that it gets to the surface of the Earth. This is what we call an illumination map. And this is really quite uncontroversial for if there's not a dominated by a single source. The cosmic rays getting to the surface of the Earth, of the galaxy of the Milky Way, would have an illumination distribution something like this. And this is just showing as a function of energy how at different energies you see further. But the observed distribution is like this. So these plots here vertically are the Auger dipole sky maps, and this is the Auger dipole amplitude. And the black is the prediction of is the data, and I think it's the yellow is the prediction of the model, but maybe it's the turquoise. I don't remember. The difference between yellow and turquoise was whether it's, I went back, I have to go backwards. I hope I can go backwards. It was whether it was all sky or just the Auger field of view. But what you notice is that you get a very good description. This is the model, and that's the data. It's extremely interesting that the Auger hotspot and higher energy could turn out, this turns out to be very sensitive to the composition, which is not accurately known enough yet to decide. It could be that the Auger hotspot is only the large-scale structure and is not a prominent local source. Or it may be that it is a prominent local source. It's just too soon to know. One thing that's interesting is that if this is the correct description of the dipole, a pure proton composition is really excluded. It's an entirely wrong direction and much different amplitude, much bigger amplitude. So my point of view is that this is the model to shoot down. It doesn't have to be true. You could have a conspiracy where a number of different local things happened to give you the same pattern that we see naturally emerge from this extremely simple model with almost no input. And so the model, I would say, the sort of baseline picture of cosmic rays is that there seem to be mostly many weak sources. As I say, the hotspots superimpose on that, then it become very, very interesting. They were interesting anyway, but this kind of tells us, for example, that they're very close. So something that's 100 megaparsecs away would not be a candidate in this, but M82, which is 4 megaparsecs away, could be. Okay, so now I'm going to shift and in the last 10 minutes, talk about recent work with, well, it's been spanned over 15 years actually, but I'm going to stress the very recent work with my student, Marco Musio. So this work started in a collaboration with Michael Unger and Luis Sancho-Torqui in 2015. And what was motivating us was that people, so I'm gonna, this is now 2019 data. And you see that by now the error bars are really tiny, and thanks to TA, we're getting, with TA and O'Shea, getting this even more detailed structure. Anyway, what had been noticed is that the portion of the spectrum, roughly speaking, if I just continued this as a bump, was pretty well described by one source class. The idea was that cosmic rays get produced in some so-called Peter cycle that is in the source. They're accelerated according to their what matters is their rigidity, and so the peak energies of different components would be smaller and smaller as they had lower charge, and that then they propagated from the source, and that got a pretty decent description. It had two in my mind. It requires a very hard spectral index, e to the -1, which is much harder than standard diffuse acceleration. It is, I mean, it's very stimulating, of course, for theorists to try to think of mechanisms that can give such a hard spectrum. The other thing is that it completely failed to explain nearly a decade, or at least a half a decade, of flux, which is undisputably there, and TA, as Sagawa-san just explained, has now beautiful data in this region. So it's absolutely no doubt that there's this component. It's light. It's not galactic. The anisotropy is in totally the wrong direction. And the question is, why does it have the same, roughly the same magnitude as the unambiguously ultra-high energy stuff? So that was what was bothering Mikhail Unger, Sancho Darkly, and we came up with the following picture. If you accelerate in the accelerator some primary nuclei with some spectrum, and they're surrounded by stuff, an intense photon field, dust and gas, and a starburst galaxy, and so on. After all, look, it's clear that inside there, let's say that's the center, that's the AGN, and that's the source. There's a lot of stuff it passes through before it gets out. Anyway, you'll have primary nuclei that were accelerated in the accelerator get broken up into things like nucleons and alphas, and then a lower mass nucleus, maybe magnesium or something if it started off with silicon. Or it might happen on gas. Anyway, this process produces secondary nucleons, neutrons, protons, and neutrons, and the pions decay to give secondary neutrinos, and with a now quite well-defined spectrum. So the argument in favor of this picture is that Occam's razor really is happy not to have to hypothesize some new source. It gives an excellent, as you can see, fit to the spectrum and composition. The composition is down here. And another tip-off that this is what's going on is that the energy of protons, if most of them come from this spallation source, will be the maximum energy that the accelerator produced divided by the maximum mass, nucleon number of that particle, not depending on its rigidity. If the protons had been accelerated as a primary part of the acceleration, then their relation of their energy to the energy of the most massive particles would be off by a factor of 2, and that fits. Okay. Here's a sort of schematic picture. Of course, that we also would then expect to see gamma rays and neutrinos from all of this. Okay. This gives rise to two different types of neutrinos, or an expectation that there will be two kinds of neutrinos, because the neutrinos coming from these cosmic rays are peaked here. This is the VHE neutrinos that come from this process by which of the interactions in the source. There's another then population which we don't discuss, could be galactic or just associated with some other mechanism at much lower, at the lower energy. So this is the astrophysical non-ultra energy cosmic ray source neutrinos. A consequence of this picture is that you produce secondary photons, but because of the absorption in the extragalactic background light, the flux is much lower. And so the photons, the gamma rays that are being detected now are from individual electromagnetic sources. And by the way, we predict the glass shower event. The other thing, and this is the exciting new work, which I think is going to have very important ramifications, is that, let me try to go back to this picture here perhaps. The key thing, the zeroth approximation key thing in this disintegration process is what's the interaction. That's the zeroth approximation. The other important one is once you allow for there to be both photons and like gas or dust in the environment. When this first work, UFA, was in 2015, we only allowed a photon environment, and now Muzio has extended that to include gas. In any case, the important thing is that different cosmic rays, these very high energy ones in here, first of all, they will escape differentially. The lower rigidity ones will be trapped longer and thus processed more. And so what it does is it creates a very distinctive feature. Furthermore, the magnetic confinement has a scale in that, which I guess I don't have a real good picture of. But I'll just tell you, there's a natural scale in the magnetic confinement having to do with the ratio of the Larmor radius to the coherence length of the magnetic field inside this source. So therefore, we get information, that scale imprints itself. Therefore, we immediately get information on the strength of the field and its coherence length. Anyway, this is a plot of the field in the sources, in the surroundings of the source, compared to its size. I want to stress this is not a Hillis plot because we're not talking about the accelerator, we're talking about the surroundings. Of course, it's got resemblances. And the gray regions are the favored regions from our analysis. And then overlaid on it are where different candidate sources sit. The whole picture can move this way if it's not a perfect black body, but it's perfectly well known how it moves it. This is just so you understand. You shouldn't start drawing conclusions about our starburst galaxies disfavored. But a conclusion like the fact that massive, large galaxy clusters is strongly disfavored, one has to do a little more analysis, but that's the kind of conclusion that we can draw. Also, one of the parameters that it will constrain is the temperature of the surrounding field. And that's very, very constraining. For example, starburst galaxies have quite low temperatures, like 30 or 50 Kelvin, and so on. Okay, so it looks like to me like my time is starting to get up. I think I have a couple more minutes. This is just repeating that plot and then showing you that we can also make a plot which for astronomers or astrophysicists, theorists trying to understand what sources can be involved, is the magnetic field times the size of the thing relative to the surface mass density. That is to say, what's the projected gas and dust, which is a measurable thing. Many of these things are hard to understand individually, but this can be measured right now. So it's the same sort of story as over here in terms of the posterior probability distribution, that's the peak. But now we have the problem that some of the candidates, which over here look quite promising, like laser flares or TDEs, over here, their properties are so badly known for now that their boxes are huge. but those will come down as people start to understand those systems better. Another peek forward, I thought of showing you a slide, but decided it was not prudent, is that there really, in our analysis, I think there's quite a clear indication of a second component in the whole story. I'll give you a teaser. It might be heavy or it might be light. Anyway, that should be coming out soon, I hope. So to conclude, I think we've found a generally correct picture that suggests that the large-scale structure is the sources are more or less continuous with important local ones. There's does appear to be a second component in Marcus and my analysis. The accelerator spectral index, by the way, is compatible with a diffusive shock acceleration. I forgot to mention that. It's because what comes out of the source is different. Because it in the magnetic field, but that hardens the source. But the fundamental spectrum, whoops, I goofed and lost it, or else you the fundamental spectrum, let's see, can I get that back quickly? Oh, shoot. I think I need to, I must have bumped my, sorry. Okay. I'm really sorry. Okay, is that all right now? I'll just finish quickly. The high energy neutrinos, we have a very concrete prediction. I wanted to stress that there's really a great potential, I think, for USOJ and TA to collaborate on trying to improve composition determinations with a scintillator scheme, and I'd love to talk to people. And then we really want to go for excellent resolution in both composition and energy to do this kind of next generation studies. Thank you so much.
Thank you very much. Any questions or comments? Please write questions or comments in the chat in Zoom or write in Slido in YouTube. I will pick some up and read them aloud. One question. Do you or will you have any update for your GMF calculation?
Do I have any what? I broke up a little.
Do you or will you have any update for your GMF calculation?
The problem is the second word. Do I have any optimism or any application?
GMF calculation, galactic magnetic field calculation.
That part I understood. You said, am I optimistic or do I have any applications? Oh, an update. Oh, sorry. Thank you.
Do you have any plan to update?
Yeah. Oh, I'm sorry. Yes. Well, I always think we're really close. Miko Unger and I have made so much progress, but somehow we're both perfectionists and we think, oh, wow, we can now do this other thing so much better. We have to do it. But we promised each other that we would try to get an updated field model out within, on the scale of months, like 2 months or something. On the other hand, friends of mine know that we've been through this before anyway. So we've both applied for grants to support students doing it. And so I think that's going to be a motivation for us to finish the first round at least. And so maybe the answer is that it'll be soon. But what I can say is remarkably, due to various, changes in the data and whatnot, the model turns out to be really robust. It's surprisingly good. Even though different things change, like WMAP versus Planck, it turned out that other things changed too, like our understanding of the cosmic ray electrons and so on. And so together, the field, and just as an accident, the JF12 model is turning out to be really quite good. From Pierre, hi Pierre, what's the importance of the galactic halo on anisotropy? Well, the halo is where a lot of field is. On the other hand, so I think that there'll be a very great synergy between Northern Hemisphere and Southern Hemisphere detection, because Northern Hemisphere, let's hope that the TA hotspot is true. I really think so, and that you get composition data in detail so you can really map out where its source might be. That will tell us a great deal about the halo magnetic field, because those cosmic rays really are coming through the halo. They're away from the galactic center, so it's more pristine. That's why the deflections aren't very big, something like 10 degrees, as you could see from my picture. When you can combine that greater knowledge of the halo, then you can infer that. So I'm pretty optimistic, but I do agree that by the way, in this analysis with Chending and Noini Globus, the overall shape of the anisotropy, especially the position of the dipole, is very substantially shifted because it goes down to 80 eV. But it's shifted by 20 or 30 degrees, maybe even 40 degrees. So the galactic halo definitely mattered a lot for that.
Okay. Thank you. So the time is pressing. So let's thank the speaker again. Well, let's move to the next talk. The next talk is entitled Probing the Universe from the Tibetan Highland, given by me myself. Okay, today's title of my talk is Probing the Universe from the Tibetan Highlands. The outline of my talk will be about Tibet AS Gamma experiment. This one is a multi-purpose experiment, so we can do many things, but today I would like to talk about two things, gamma-ray observation and sun shadow observation. And finally, summary, if I have time. So let me introduce you the observational energy today I'm talking about. I will talk about 1 beta electron volt, 1 PeV sometimes, or sub-PeV. Sub-PeV is 0.1 PeV to 1 PeV. So say 1 PeV is, for example, the gamma ray of 1 beta electron volt energy has 1,000 trillion times more energetic than visible light, the light you see. And about the Tibet AS Gamma experiment, this one is a collaborated list of the Tibet AS Gamma experiment. The AS Gamma is the abbreviation of air shower gamma ray maybe. And this is a joint experiment between China and Japan, and which is composed of roughly 100 researchers. The Tibet AS Gamma experiment is located at Yanbazin, Tibet, China, at the altitude of 4,300 meters. Why so high? Because cosmic rays are absorbed in our atmosphere, if you observe them at the sea level. That's why we have to climb up to highland. and high flat land we need because our air shower surface detector array, the area is roughly 65,000 square meters. And this air shower array is composed of plastic scintillation detectors. Plus, another component of our experiment is the underground muon detectors are of 3,400 square meters in area. The detection principle is cosmic rays hitting the Earth interact with nitrogen mostly and they produce a lot of secondary particles. So these are called air showers. So the shower particles are composed of electrons, positrons, gammas, and many things, neutrinos. And the secondary particles hit our detector, light sensor, light detectors. Each detector is a plastic scintillation counter, plastic plate here, and when a charged particle goes through the plastic plate, it scintillates, emit light. Then the light sensor photomultiplier 2 detects the photon. And we can determine the direction of energy of the gamma ray or cosmic rays using the timing information and the pulse height, light timing information and charge information or light quantity information. So the shower particle is like a plane. So counting up all the hit PMT photomultiplier tube information, pulse height, then it is proportional to the energy of primary particle. And you see the relative timing difference between the detectors will tell us which direction the primary particle comes from. And important thing is air shower array can determine the primary particle energy and direction, but cannot separate from gamma rays from cosmic rays. So we set up constructed large underground muon detectors. So you see, this is air shower, and we enlarge around here, ground. So see, the upper figure shows the 0.2 PeV gamma rays hitting the Earth, the air shower induced. Sorry, the gamma ray induced air shower hits the ground. Then it looks like this, and the lower figure shows how it looks when air shower is induced by cosmic rays like proton. So the difference is, you see, in the underground, you see many muons, blue lines. So it is very simple to separate gamma rays from cosmic rays. Construct a large underground muon detector and count the number of muons. And mirrorless air showers are gamma ray induced air showers. That's simple. So I'll talk about gamma ray observation now, especially diffuse gamma rays from our galactic plane, not from point source object like a star, no. If we cut very tightly the background of cosmic rays, we can select gamma rays. You see, this is our galactic plane. And before cutting our events, before selecting gamma rays using our underground muon detectors, the event map looks like this. There are many events. These gray areas are out of our sight. So we can reduce cosmic ray back background down to 1 part per 1 million around in the sub-PeV region, then our galaxy looks like this. You see, there are many events aligned on the galactic plane. These are consistent with the background, cosmic background. So just forget those events. This is the first detection of sub-PeV gamma ray from the Milky Way galaxy. See, this is our galaxy. Galactic center is here, and our solar system is located in the Orion spool. And sun, our galaxy contains 100 billion stars, stars like a sun, and they are distributed in the disk, galactic disk. Our galaxy is, when we look at our galaxy by radio, then we see atomic hydrogens along our galactic plane. And if we see galactic plane by optical light, we see stars. And if we observe the galactic plane by X-rays, then hot plasmas we see. And if we look at our galactic plane by the highest energy gamma rays, it looks like this. You know, these are signals. We observed 23 ultra high energy gamma ray events along the Milky Way sub-PeV region. And the highest energy amounts to roughly 1 PeV. Our galactic plane is here. Oh, no, center is here. And galactic plane here. These areas are out of field view at Tibet. That's why we need this kind of experiment in the southern hemisphere, like say Alpaca, Professor Kajita introduced to us earlier at this event. So anyway, let's move to the scientific interpretation of the data. So the cosmic rays were discovered by Victor Hess back in 1912. Hess, you know, this guy is Hess, and they measured the cosmic radiation, you know, using ionization chamber. Anyway, like a radiation counter, and when they goes up 2 kilometers, 4 kilometers, and 5 kilometers, the radiation rate goes up. That's why they concluded the cosmic ray comes from our universe, not from the ground. And cosmic rays hitting the Earth produces air showers. They composed, cosmic rays are mostly composed of protons. And cosmic ray, where do they come from, the origin? Sun or supernova remnant or active galaxy? The most probable candidate is supernova remnant. We guess now. Supernova remnant is death of a star, you know. And this one is an energy, cosmic ray energy spectrum. Energy versus number of particles. Anyway, one is 1 PeV. So, you see, there is a band around 4 PeV. The rapid decrease of cosmic rays was discovered in 1958, and this is called knee. You know, this looks like a human knee. And we think cosmic rays below knee energies are believed to be of galactic origin. That means supernova explosion origin. And above knee, the cosmic rays are of extragalactic origin. They believe, or we believe. And as an open question is, did or do pevatrons really exist in your galaxy? A pevatron is a cosmic ray super accelerators, accelerating cosmic rays to beta electron volt. And cosmic rays with electric charge are bent by the magnetic field in our galaxy and lose their direction. However, gamma rays without charge, electric charge, cosmic rays interact with interstellar gas, then produce gamma rays, and gamma rays go straight, unaffected by magnetic field because they are chargeless, and they point back to the sources. And despite exhaustive searches for pevatrons over the last 20 years, researchers have no conclusive evidence yet. So this is a mystery of 60 years in cosmic ray physics. And let's go back to our event. You know, they are distributed along the 23 events distributed along galactic plane. So these highest energy gamma ray events, including 1 beta electron volt event, are discovered to be spread out along the Milky Way, you see, rather than known gamma ray objects. Gamma rays coming directly from the object are difficult to identify cosmic ray proton origin, since they could be gamma rays produced by collisions of electrons with photons. So, you know, electrons interact with magnetic field and radiate synchrotron radiation. Then they soon, so electrons lose their energy very quickly around the source. So they should stay near the source. On the contrary, protons do not undergo synchrotron radiation. They don't lose their energy. They can escape farther from the object, the source. So they can be diffused. So you see, the gamma rays are coming from isolated from known gamma ray sources, these yellow points. So that's why this is a strong evidence for sub-PV gamma rays induced by cosmic rays, not by electrons. This shows the pevatron and cosmic ray pool. You know, we are not 100% sure, but the most probable cosmic ray origin is believed to be supernova explosion, which occurs every 30 years in our galaxy. And in the supernova remnants, cosmic rays are accelerated within 10,000 years after explosion. They become pevatron. Then cosmic rays has been trapped by the galactic magnetic field more than a few million years, forming a cosmic ray pool like this. So they accumulate roughly 100,000 supernova explosions, you know, cosmic ray pools. And when supernova occurs, cosmic ray produced and accelerated like this, and PEB cosmic rays. Then PEB cosmic rays interact with interstellar gas, and that is a proton mostly, and produce gamma rays. These total gamma rays have typically sub-PeV energy range, 1 order of magnitude lower energy compared to the parent proton cosmic ray. So if PeV cosmic ray exists, sub-PeV gamma rays are expected. You see, we detected sub-PeV gamma rays along the plane, galactic plane. So this is the first compelling evidence for existence of pevatrons in the past or in the present galaxy, because the cosmic ray pools are composed of the accumulation of cosmic rays, say during the million year or 0.1 million year and so on. And the pevatron accelerate protons up to the beta electron volt region. So this is the explanation of how sub-PeV cosmic, how sub-PeV gamma rays are produced. High energy cosmic ray interact with galactic hydrogen, then makes this sub-PeV gamma rays. So this work proves a theoretical model that cosmic rays produced by pevatrons are trapped in the galactic magnetic field for millions or 0.1 million of years, forming a pool of cosmic rays. And well, how much time? Maybe. So I would like to move to the sun shadow observation. The cosmic ray casts the sun shadow in cosmic rays. Because the sun has finite diameter, the cosmic rays are shielded by the sun. So we observe sun shadow in cosmic rays. And you see, there are magnetic field between the Earth and the sun, so that this shadow can move the position dependent on the 11-year period of solar activities. The position changes and the depth changes also. So this is a change, yearly change of galactic cosmic rays. Sun shadow, deep shadow, and shadows, shadow. And the cosmic ray sun shadow has anti-correlation with solar activities. So when solar activities come, the shadow becomes dark. And when solar activities becomes very hot, the shadow goes away. So it is a very good probe of solar activities. And we observe such cosmic ray sun shadow. And this, there is a coronal mass ejection. This is a big explosion from the sun, and the plasma can, can come reach the Earth. Very energetic phenomena, and sometimes GPS information might be changed, or the astronauts outside of the International Space Station might be hit by such energetic plasma. So space weather forecast is important, So CMS takes cosmic coronal mass ejections takes 4 days from the sun to the Earth, while cosmic ray takes only 8 minutes. So when if the very energetic coronal mass ejection phenomena occurs, hot plasma comes to the Earth, then sun shadow might disappear. So the sun shadow could forecast space weather in principle. So this is the summary. So the time is pressing. Thank you for your attention. Well, any questions and comments?
I have a question. Should I just ask it? Unfortunately, a helicopter just went over.
I can read your question. Because proton is heavier than electron, proton doesn't lose energy by magnetic field, right? Yes, you are right. You are right. The synchrotron radiation cross-section is probably proportional to the mass inversely square of mass square, inversely proportional to mass square. I guess I'm not a theorist, so I just learned it in the textbook long time ago. But you're right.
I have a question. Should I just ask it?
What?
Do you have a plot by any chance of the distance a typical proton has gone from its source where it was accelerated, let's say in a supernova remnant, before it makes its photon? There's so much more mass right in the environment, I would think, of the supernova that you might. I just wondered if you should think of the protons as being in some random position when they interact with gas and make your PeV photon, or whether they might be near their source.
Well, but you know, we checked the position of our gamma-ray event and the known TeV gamma-ray sources, TeV gamma very energetic sources. But within, say, within 1 degree from the source, known TeV sources, only one event we observed. You know, if they were produced by electrons, they should be located around the source, energetic source, within 1 degree. But we don't see such signal. Okay. Typically, electron can separate from the source by roughly 102. Okay. Well, if not, how far? Oh, typically, how far physical distance? Not angle. Oh. It's typically 1 kiloparsec times 1 degree. 1 degree. So 1 kilo, a few kiloparsec over a few 60. One radian, radian is 60. So divided by 60. So
I can ask you later. Sorry.
20 parsec.
It's okay. It's okay. I'll ask you later. We can do it offline.
Mm-hmm. Well, if no more we would like to move to no next session, coffee break. So, Sagawa-san, 10 minutes. We are right. So shall we start the next session as it's scheduled, or shall we start a little bit later? As scheduled. Okay. Okay. Then the next session will start as scheduled. That is 15:15. So the Boston, we arranged the Boston session during the coffee break, but it may be difficult to join the Boston session. So the next session will start, the final session, start as scheduled, 15:15. Thank you. Well, good afternoon. The final afternoon session starts now. The first talk is entitled A Brief History of LIGO and Gravitational Wave Experiments, given by Principal Investigator Peter Pritchard from MIT Kavli Institute. Principal Investigator. Now, Peter Pritchard, please.
Yes, hello. Can you hear me okay? And you can see my screen?
Yeah, but not full screen mode yet.
Yeah.
Oh, yes,
Very
yes.
Okay.
Okay.
Let me get a pointer. Good. All right. Well, good. Hello, everybody. First of all, thank you to the organizers for inviting me to talk at this symposium. So I was asked to give a brief history of LIGO and other gravitational wave interferometers. Obviously there's a lot of history there over the last kind of sort of 50 years worth or so. So this is certainly a very select sampling, I would say, of the history. And I will talk about a little bit about other gravitational wave interferometers, but it'll be heavily focused on LIGO. So before I get into the history part, I've got a few slides of just background information. I think that will be useful to cover first, since not everybody's an expert. So in terms of gravitational wave basics and the basics of gravitational wave interferometers. So gravitational waves were recognized by Einstein as coming out of his theory of general relativity in 1916, a year after he came out with his theory of general theory of relativity. You can think of it as a sort of necessary consequence of special relativity with its finite speed of light or of information transfer. And it's certainly one of, if not the most sort of distinctive departure from Newtonian theory. So gravitational wave is a time-dependent distortion of space-time that would be created by acceleration of masses. They propagate at the speed of light, at least in general relativity, they propagate at the speed of light. And the wave strength is characterized by a strain in space, which is usually denoted by the symbol h. They're transverse waves, and they have two polarizations. So and you can see they kind of have this quadrupolar nature. And so as the wave is traveling in one direction, the strain will have, say, a positive sign and effectively increase distances. And then the orthogonal transverse direction will have a negative sign and sort of effectively decrease distances. And then that switches, in the other cycle of the wave, and then, sort of back and forth. So that's sort of the nature of the gravitational wave strain as it propagates through space. So detecting them then with interferometry, you can kind of see that, that gravitational wave strain, we use a Michelson interferometer, where sort of the defining characteristic of a Michelson is that, you have a light source. Of course, we're going to use a laser for that. And you split it into two halves with a beam splitter, and then they go down arms that are orthogonal. They don't have to be orthogonal, but they are orthogonal in our detectors. And then those beams come back and recombine at the same beam splitter that they were originally split off at and interfere there. And you can see that's nicely, the geometry is nicely matched to a gravitational wave. If it propagates through, the gravitational wave is going to effectively decrease the distance in one arm while it increases the distance in the other, and then vice versa as the wave cycles. And of course, that'll vary the interference of the beam splitter and create a signal in the photodetector. So you can see that, again, the wave itself is characterized by the strain h, which, think about it then in terms of the detector, is going to create a change in the length of one of these long arms proportional to the length. Each arm gets changed by amount, which is the strain times the length divided by 2. And to give kind of a scale of things, for our LIGO detectors, we're 4 kilometers long in each arm. As you'll see, the strain that we sort of target is 10 to the minus 21 or smaller, that we're looking for length changes of 10 to the minus 18 meters or smaller. And that's what the interferometer is designed, it has to be designed to do. Sort of interesting, maybe a historical note, we use these numbers to introduce, the topic talks like this for many, many years, decades, sort of, 10 to the minus 21 as the target. And as it turned out, as you'll see at the end, in fact, for the first gravitational waves we detected, the strain really was right. It was 1 times 10 to the minus 21. So it's a very, very good example to have used. The core challenge, right, for gravitational wave interferometers is understanding the detector noise and reducing the detector noise. So we typically plot that with a spectrum like this, the spectrum of the detector noise. This is the amplitude spectral density of the detector noise output channel, but expressed as the equivalent gravitational wave strain H that would create that noise. So think of it as the square root of the power spectrum of the output of the detector. And you can largely separate the different types of noises into 2 categories. One which would be displacement noise. So these are things that move the actual test masses of the interferometer, things like seismic noise, thermal noise, radiation pressure from the light that's in the interferometer. On the one hand, and the other hand, sensing noise. So even if your test masses were noise-free, completely stationary, there would be limits to how well you can measure the distances due to photon shot noise, residual gas noise, stray light can come in and create noise. So those are some of the typical things that create what we call sensing noise. So this is sort of just sort of the basics of gravitational waves and gravitational wave interferometers for detection. And now I'll launch into the historical aspects. So, one question, people ask, who invented the gravitational wave interferometer? I think the answer is many people did at different times in different places. The earliest suggestion of the concept of using an interferometer to measure gravitational waves is apparently from 1962 in this article a pair of Russians published, Kirchenstein and Pustovoy. It was actually translated into English shortly after 62, but it wasn't actually widely known in the West until sort of the late 1970s. Although it was noted by Vladimir Wikinsky in 1966 in one of his articles. But so it was just conceived of independently, right? There's several others in kind of the mid to late 60s and early 70s. And a couple of prime examples here are Robert Ford, who was working at Hughes Research Laboratory, and he actually built what we think is the first interferometer, gravitational wave interferometer at Hughes Research Laboratory. It's kind of a curious place to do it. But it was a small scale, sort of meter scale arms that he built in the 70s with a helium neon laser. One of the real curiosities of the paper, as a Rev D paper, is that he did his data analysis by listening to the output. And so there's a section 7 of the paper, as a heading, calibration of the ear. So they thought they could hear frequencies in the 3 to 10 kilohertz region, and they thought they had sensitivity about 10 femtometers at that time. So 10 to the minus 14 meters. You can keep that in mind because eventually, right, we need to get to about 10 to the minus 19 or 10 to the minus 20 meter sensitivity. But then the realist we think of sort of in many ways the founder of the field was Ray Weiss at MIT. So he had the concept kind of in the late 1960s. So many of us cite as kind of the beginning of the field is an analysis that Ray Weiss did in the early 70s, and he published a technical report in April of 1972, and this was really, he published it. He didn't think it was worthy of sort of journal publication. He just published it in the quarterly report of MIT's Research Laboratory for Electronics, and this is really the first time sort of there are detailed noise analyses and sensitivity analyses of the interferometer, where he actually addressed quantitatively the shot noise, radiation pressure noise, thermal noise, seismic noise, and all that, and made some comparisons of the sensitivity to actual potential specific astrophysical sources of gravitational wave. This is really, we sort of, many of us think of this as kind of the starting point of the field in 1972. So then what started sort of over the next decade, there kind of in the 70s, there are 4 groups really that formed to try to use this interferometer technique for gravitational waves, right, gravitational wave detection, and built prototypes. So those 4 groups were, so at MIT, Ray Weiss, and eventually it got kind of a slow start after the 1972 article, but eventually they built a 1.5 meter long Michelson interferometer using delay lines in the arms. I'll say a little bit more about what that means. And then also at Max Planck Institute in Garching, a group got going, heard of the idea and thought it was exciting, and they were actually able to move forward more quickly in the 70s than any other group. And again, they used this delay line design to initially build a 3-meter prototype, but then fairly quickly followed by a 10 times longer 30-meter prototype in 1982. The University of Glasgow got started with interferometers with Ron Drever with a 10-meter prototype that began about 1978. That didn't use these delay lines. Ron Drever heard about problems with scattered light that was happening in this Garching instrument. And he had an idea to use Fabry-Perot cavities in the arms rather than delay lines. So they got started with that. And then later at Caltech, well, in the early to mid 70s, Kip Thorne had a theory group at Caltech that was starting to look at gravitational wave sources and ideas for detection. But just a theory group, and he thought it would be appropriate eventually towards the late 70s to form an experimental group. And so that was formed in 1979, bringing Ron Drever from Glasgow. And then they began building a 40-meter long prototype in 1981. So kind of just a quick survey of those prototypes in the 1980s. So again, I kind of said, there are these 2 types, 2 different ways to store the light in the arms and increase the interaction time of the light with the gravitational wave. So the first one was this delay line concept, where you just take the laser light and bounce it back and forth many times, sort of discrete times between 2 mirrors in each arm. And that, again, was done both at the MIT 1.5 meter prototype and in the German 30-meter prototype. And I'm just showing here some of the spectrum. They typically in those days, they would be expressed not in terms of strain, because these were short, and so the strain was going to not be very, very, very small or very interesting. So they did it in terms of the displacement noise of the interferometer. And again, eventually we're going to be needing something in the 10 to minus 19 meter per level, and down at like 10 hertz, or not 10 hertz, but 100 hertz. So you can see these early prototypes were very, very far from that. The German one was the best performing one in the 1980s. And you can see these delay lines made nice. So the drawings here are showing just maybe like 4 passes. Even this one is showing a few more, but in reality, they would be constructed with tens of passes. You can make these nice, pretty pictures of the multiple beams on the mirrors. But they did suffer with problems with scattered light, where the scattered light would, all these the mirrors would scatter light to some degree, and then that scattered light would kind of stay in the system and pick up noisy phase shifts that would create noise in the interferometer. So by the late 1980s, all groups had gone over to this Fabry-Perot technology, where there's a resonant Fabry-Perot cavity in each arm. So it's much better from scattered light control. It was also better in terms of thinking in the longer term. If you're going to use delay lines with a multi-kilometer detector, you would need much, much bigger mirrors, because you've got these discrete spots that are arrayed around the mirror. Whereas you can think about the Fabry-Perot as kind of taking that concept, but coalescing all those beams down to one spot, so you don't need as big of a mirror. But both the Glasgow and the Caltech prototypes in the 1980s were using that Fabry-Perot technique. Although for much of that time, actually, interestingly, neither detector used what we would call a Michelson interferometer, in the sense that the laser beam, yes, was split between the 2 arms. There'd be Fabry-Perot cavities in each arm, but then the beams weren't actually recombined on the beam splitter to make a Michelson. They were detected independently from each arm. So like typically one arm would be used as like a reference arm, and then you'd compare it, look at the relative noise in the other arm. So in that sense, they weren't true Michelson interferometers. So that took a little bit longer. Yeah, here's just kind of a graphical sensitivity progression throughout the 1980s. Again, showing displacement noise. And again, it's at high frequencies, at 2 kilohertz, because they just weren't very sensitive at the lower frequencies that are actually relevant. But again, you can see like by the late 1980s, is really this Munich 30 meter that was the best sensitivity, had the best sensitivity of them. But clearly everybody knew, that you need really a long multi-kilometer detector to get into the game of actually detecting gravitational waves. So starting at MIT, kind of in the early 1980s, there was a sort of the first real science and engineering study of what it would take to make a long baseline interferometer was carried out. And then in roughly the mid-1980s, MIT and Caltech started to collaborate on what would then become LIGO itself, on collaborating together to propose that project. So the actual construction proposal for LIGO then was completed in 1989 and submitted to the National Science Foundation. So it consisted of 2 volumes, one which covered the science case, the detector physics, the noise analysis, and the prototype experience that had been had up to that point. Then the other volume focusing on the engineering design and the cost estimates. The other thing that was important about that proposal was that it defined sort of the phased approach for LIGO in the sense that the proposal was to build these observatories and to put in like an initial set of detectors that were fairly simple, but the idea being that there would be then multiple generations of better and better detectors installed in these observatories once you got the big facilities constructed. And then this was the sort of the noise we call the noise budget for those first initial interferometers that were proposed in that 1989 proposal. So it took a few years before the proposal was funded by the National Science Foundation. But the construction then began in 1994. And NSF had selected two sites for LIGO, one in Washington State, so the northwest corner of the US, and then one in Louisiana between New Orleans and Baton Rouge. And of course, you want a nice long separation between the 2 detectors because you're going to use the time of flight or time difference information to figure out where the gravitational wave is coming from through triangulation, because each detector itself is pretty omnidirectional in terms of its sensitivity. So the 2 observatories were constructed over about a 6-year period. There are actually 3 interferometers made for initial LIGO. At Hanford, it contained both the long 4-kilometer detector, and it also had what we call a half length or 2-kilometer long detector. Whereas Livingston had just 1. And then, so in what we call initial LIGO then, the initial LIGO detectors operated from 2002 to 2007. Then there were some enhancements we did, we call enhanced LIGO, that operated for a couple of years from 2008 to 2010. So it reached, so LIGO, initial LIGO reached its design sensitivity eventually in 2008. It took a lot of data, although no gravitational waves were detected in those data collection runs. So here's an aerial photograph of the LIGO Hanford Observatory, sort of high desert territory outside of what's called the Tri-Cities in Southeast Washington State. This is the LIGO Livingston Observatory. So it's, it's basically identical observatory. The local terrain is very different, obviously, but otherwise they're designed to be identical. Here's a shot of the beam tubes under construction. The long arms, of course, are constructed of a 1.2 meter diameter stainless steel tube, which of course has a high vacuum in it. And they were designed actually for the vacuum level that you'd need in the future as more and more sensitive interferometers would be installed. So they're designed to reach a level about 1 nanotorr. And the other thing is you have to design the tube so that the scattered light that's going to come from the mirrors is going to scatter off the tube, and you don't want that to create excess noise. So again, that was designed the way that the scattering was, baffles and so on that were designed for the tube. It was designed again with the future in the sense of looking at the sensitivity that you'd need for future interferometers. Similarly, with the vacuum chambers that hold the test masses and the other optical components, they were designed, I mean, to some degree, to be able to accommodate larger test masses in the future for later, better detectors. But for the initial LIGO interferometers, really the philosophy was to start very simple in terms of the actual detector design, because things were going to be difficult enough scaling up by a couple of orders of magnitude from the prototypes that we had. So we wanted to keep the technology of the specific detector components as kind of as simple as possible and as proven as possible that we had done up until that point in the prototype. So for example, the seismic isolation for the test masses, just a simple set of masses and springs, you know, a cascade set of masses and springs that provide passive isolation. And then the suspension for the test mass itself, which is a 10 kilogram cylinder of fused silica, that was suspended as a pendulum just on a single stage of pendulum on just a loop of steel wire that goes around the cylinder and suspends it. So again, just keeping things very simple for the outset for initial LIGO. One thing that turned out to be not quite so simple initially was getting the mirrors of the test masses actually made. I used test masses and mirrors interchangeably at various times. So the issue here was that the test masses and the mirrors had to be polished, you know, to very good, to be spherical surfaces to a very high degree. But initially we didn't really realize that. So for example, in the original proposal, that specification was put down as lambda over 25. But with later modeling over the next sort of 3 or 4 years, we revealed that needed to be tightened up quite a bit to lambda over 1600. So quite a bit. And so the challenge really was, once we started to look at whether the optics industry, there's a big worry at this point whether the optics industry could actually produce that. But we found that they actually could do it. And not only could they do it, but they were already doing it. They just didn't really know it because of the metrology wasn't quite good enough. But that turned out to be a nice success story. Similarly, the coatings that are put, these are, you know, the fused silica substrate is coated with layers of dielectric to make the mirror properties. And those also had to push the state of the art in terms of low scatter, low absorption, and uniformity of those coatings. So eventually, it took us a long time to get to design sensitivity, as you can see by the progression of these noise curves. But as we were doing that, as we were, you know, improving the detector to get to design sensitivity, we took discrete science runs that lasted, you know, a few weeks to a couple months, and then eventually, once we reached our target design sensitivity in our 5th science run, we took it ran close to 2 years to get 1 year worth of integrated data. And at that point, the detectors, another way to look at the sensitivity, in addition to this noise spectrum, is to say, well, how far out could you measure a particular source? The source that we would use is the merger of 2 neutron stars. So these detectors at that point were sensitive to measuring the merger of 2 neutron stars out to about 14 megaparsecs. Also interestingly, maybe particularly for this crowd, is some of the early runs with initial LIGO and data analysis were carried out with TAMA 300, which was a 300-meter interferometer that had been built at NEOJ in Tokyo. You know, much less sensitive, of course, given that it was, you know, more than 10 times shorter. Because they were included at the beginning. So yeah, this is then just showing reaching the design sensitivity for initial LIGO. So we had, you know, we're able to be sensitive to sort of strains of you know, several times 10 to the minus 22. And so even though we didn't detect anything, what we did do during that period was write lots of papers on upper limits of bursts, upper limits on stochastic, background of stochastic gravitational waves, upper limits on coalescences, et cetera, even some papers on, you might have seen flash by, some interesting papers on just the quantum mechanics, the quantum physics of the detectors. But so that was initial LIGO. Now, what's going on at the same time in other gravitational wave projects? There was a British-German collaboration, geo-collaboration, that constructed a 600-meter interferometer near Hanover in the late 1990s, and that's still in operation. And that became and continues to be an important test bed for some of the technologies like signal recycling, advanced suspension, squeeze light, although hasn't actually been part of the making actual gravitational wave detections. But then more importantly, maybe the French-Italian Virgo project built a 3-kilometer interferometer near Pisa, and the construction of that was started in 1996, was a few years behind LIGO. But the design of it was very similar to LIGO in terms of the interferometer detector design, except in one area where it had a very different seismic isolation system than LIGO did. And then, so now we're moving on. That was the story of initial LIGO, moving on to advanced LIGO. The goal of advanced LIGO really to put in detectors that would have 10 times better strain sensitivity, really over a very wide frequency range. And not only have sort of 10 times lower strain noise, but have that down to much lower frequencies than initial LIGO did. And so whereas initial LIGO might be able to see those, those inspirals of neutron stars from 15 to 20 megaparsecs, we're shooting for more like 200 megaparsecs for advanced LIGO. And of course, what that factor of 10 in strain sensitivity means is that you're now probing 1,000 times larger volume of space to be much, much more sensitive to sources in our nearby space volume of the universe. And that's done, the idea was doing that with, first of all, much better seismic isolation for low frequencies, reduced thermal noise or reduced Browning noise at the mid frequencies, and reduced quantum noise through higher laser power, et cetera, at those frequencies. So in terms of the seismic isolation, it became an active system. So if you remember that simple stack of masses and springs for initial LIGO, it's now a much more complex system where you've got lots of active elements, inertial vibration sensors, actuators to make 2 stages of each of which have 6 degrees of freedom active isolation, which is now in the vacuum system. And then it's from that active isolation that then the mirror suspension is supported. So you can see how that system works very, very well. So the ground, this is a blue curve showing a spectrum of the motion of the ground. And then the red curve is showing the spectrum of the motion of this active platform. So you can see at 1 hertz, for example, we're suppressing the ground motion by 3 orders of magnitude. So sort of this large band, which is very, very helpful in terms of being able to control the interferometer. And then in terms of suspensions, that become more complicated as well. Of course, we move from a single sort of stage pendulum to now a 4-stage pendulum. You can see 1, 2, 3, 4. The test mass being at the bottom of that. So that gives you much greater degree of passive isolation of vibrations. That once you get down to the bottom, in this photograph, the test mass is down here. It just got a protective cover on it at the moment. The other change, a big unique thing, is that rather than suspending the test mass by a steel wire, it's suspended by a fused silica fiber, because fused silica has much lower thermal noise than steel does. So there are these very thin fibers, 400 micron thick thin fibers that are, you can't really see them in this photo, but they're suspending the test mass from the stage above with about 60 centimeters of that fiber. And of course, we have bigger test masses. So we went from 10 kilograms in initial LIGO to 40 kilograms. Again, fused silica. One of the things that allows us to do is make the beam bigger. So the beam is being increased from 8 centimeters to 12 centimeters. That helps reduce thermal noise. And this is showing one of the advanced LIGO test masses being measured in the metrology lab at Caltech In addition to the bigger masses or the bigger test masses, we also have better coatings for the mirrors, lower loss, both in terms of mechanical and optical loss. So for the timeline for advanced LIGO is the following. We basically started installing all that stuff in late 2010, and the installation was sort of a 4-year period, and then started integrating components of it and started to commission the detectors. There are these milestones where we call the first time you lock the interferometer. That's the first time everything is under control and you can actually start to get a signal out of it as an interferometer and start to work on the sensitivity. So that occurred. That was by plan. It was staged to happen at one interferometer before the other, or mid-2014 in Louisiana, and then about 6 months later. So once we had the interferometers installed and started to lock, we can then commission them and start to work on their sensitivity. And so what this is showing is the sensitivity now using that metric of the how far away can you see a binary neutron star merger in terms of megaparsecs. So again, the initial LIGO, the sensitivity of the initial LIGO is down here somewhere. But this is showing the progression during the commissioning period that it went much more quickly than it did for initial LIGO. So we had set a goal that we want to start collecting data in our first observing run. We're not calling them observing runs, somewhere between 40 and 80 megaparsecs. And it was very easy to get into that range. In fact, close to the upper end of that range after about 16 months of commissioning. And the second one, the Hanford one, benefited from the experience we had in the first one, so that it went even more quickly. And of course, then, right, we were rewarded by that, right, pretty much right away as we started our first observing run in September of 2015 by, capturing the signal from the coalescence of 2 black holes on September 14th, 2015. And so that was the merger of a 36 solar mass and a 29 solar mass black hole, which formed a 62 solar mass black hole. Of course, missing mass there of 3 solar masses is what was emitted as gravitational waves. So 3 solar masses worth. And again, as you can see, this is showing the actual detector data. It's been bandpass filtered to just around the frequencies of interest around 100 hertz. You can clearly see the chirp signal of the merger. And again, as I said, it ended up being that 1 × 10⁻21 strain that we had always sort of used as our target. And of course, then we announced to the world in February of 2016. It had been just as we published the paper on it in PhysRav Letters. And of course, that became front page news around the world. Thankfully, also by that time, we had detected a second merger on December 26th, 2015. So if there is any doubts as to the first one at that point, that helped bolster people's confidence, I think. Then the next historic event, I think, was in August of 2017, when we observed or captured gravitational waves from the merger of 2 neutron stars, right? And of course, we're going to hear a lot more about that, I think, in the next talk. So I think here I'll just point it out in terms of the historical story of LIGO history. Of course, and then the other unique thing about it is that Virgo contributed to this detection, or localization, maybe more properly said. I think we'll hear more about what was learned about that detection in the next talk. But of course, that's also different from, we had detected many binary black hole mergers up to that point. But of course, the interest of the binary neutron star merger is that there will be electromagnetic radiation given along with that, and of course, which was seen by many telescopes. And then, nicely soon after, continuing the history of 2017, just a couple months later, in October 3rd, we had the nice announcement that the Nobel Prize for that year was given to the gravitational wave detections to Ray Weiss, Barry Barish, and Kip Thorne. We were all gathered around early that morning at MIT, and before they actually said what the prize was given for, I think the first words that the the person in Stockholm said was, we're giving the prize this year to a discovery that shook the world. As soon as they said those words, we knew that it was coming for the gravitational wave detection. All right, so I'm just gonna end with what the picture looks like today, kind of bring the history up to date. And again, I think you'll hear more about this in the next talk. But so now we've had 3 observing runs that we've completed with LIGO and Virgo, and this shows you in one full graphic all of the detections that we've made. They're all mergers of compact objects, and the way this graphic looks is all the blue circles are black holes. So each sort of vertical icon here represents a merger. So the two, this would be a merger of sort of 8 solar masses with 12 solar masses, making something a little less than 20 solar masses in the end. Then the orange ones are neutron stars, so 2 neutron stars merging to form either a neutron star or black hole. And this is actually laid out chronologically, right? So this would be our first detection back in 2015. And at this point, I think we have 90, close to 100. It's 90 of these detections. So that kind of is a quick run through the history of LIGO. So thank you for listening, and see if there are any questions.
Thank you very much. Are there any questions or comments? Please write questions or comments in the chat in Zoom or write in Slido in YouTube. I will pick some up and read them aloud. Questions? Comments?
Maybe I'll ask a question and
Yeah.
just say thank you so much. That was a totally wonderful talk, and it was really especially wonderful to hear about the sort of the early evolution, which one tends to, it all gets glossed over, but it's really very interesting. I wanted to ask you, will there be an upcoming big sort of new news coming out, or how does it come? How does it come? Is it sort of continuous now?
Yeah, well, I think, so like I said, we've completed 3 observing runs at this point. The last, most recent observing run, we ended at the end of March 2020, because we were going to end it anyway in April, and we ended it a couple weeks early because of the pandemic. But and we haven't done any more observing since then.
Awesome.
So, and then pretty much everything that we detected from the most recent run 03 has been announced at this point. You'll probably hear more about that from the next talk. But so nothing major new coming out soon, but we are hopefully we're targeting that we'll start our next observing run at the end of 2022. So and again, we're hoping, we're planning on, we're working on the detectors being even more sensitive. So that would mean, more detections, a higher detection rate. I mean, there are 2 things that come along with making the detectors more sensitive. One will be a higher detection rate, and then the other thing is that for a given, we'll get a higher signal to noise for a given event that you can then learn more, with a higher signal to noise ratio. So yeah, I guess stay tuned for about a year from now.
And it's really, the shutdowns are in order to do installation of the upgrades. Is that mainly right?
That's right. Yeah. So we're putting in new equipment of various sorts. Yeah. Mm-hmm. One of the for the next observing run, one of the I didn't really get a chance to talk about the fact that the last observing run, we started to use a new technology called squeeze light injection. So we're actually injecting squeeze vacuum into the output port of the detector, which helps reduce quantum noise. And then the next observing run, we're kind of upgrading that system by putting in something called a filter cavity that lets that squeeze light injection work better over a broader frequency range. That's just one example of things that we're putting in. So yeah, there's always ideas on how you can make things better, but it takes time.
Okay, thank you. Let's thank the speaker again.
I see there's one more question in the chat.
One more question?
Yeah, I can answer the question in the chat. So why did you plan 2 detectors in Hanford initially? Yeah, so initially we had, so the initial LIGO, so we were planning a few reasons. So the main reason was to get, nobody had detected gravitational waves yet directly. And so we wanted to be really confident in our detection. So we wanted to have, more than just 2 interferometers. So in fact, if you can see the signal in 3 interferometers, that would just give much more confidence to the detection. And we made the 3rd one half length because we probably wouldn't do it that way again, but the thinking at the time was that the signal in the half length interferometer, if it's from a real gravitational wave, should be half the amplitude because of the, just because of the length. And so that would be like another discriminant that it's actually a gravitational wave rather than some other local disturbance. In any case, so that's why we did the 2 detectors in Hanford. We don't have 2 detectors in Hanford anymore for advanced LIGO. Just one in each place.
Thank you. So no questions anymore. Then let's thank the speaker again and move to the next talk. The next talk is entitled Current Status and the Future Prospect of Multi-Messenger Gravitational Wave Astronomy, given by Professor Peter Schoen from University of Maryland. Now, Professor Peter Schoen, please.
All right, thank you. It is amazing, isn't it, how far we've come in terms of detecting gravitational waves. I mean, the initial attempts were simple, as they had to be, and we've built up the sophistication for that. But we've heard a number of great talks today on really advanced instruments of different types for measuring astrophysical signals. And one of the things that strikes me in seeing these descriptions of these modern projects is how, in many cases, there are different components that are working together. There are different size telescopes in Cherenkov telescope array with different goals. There's, combination water tanks and scintillators and different station types and so on. And it's because at the level that we can do things now, the complementary capabilities of these fit together to make an instrument which is more capable overall. And really, that's what multi-messenger astronomy does, is to extend that beyond a single project to the worldwide set of different facilities and projects that we have. So I'm going to tell about multi-messenger astronomy with gravitational waves. That's my focus as a member of LIGO Scientific Collaboration, working together with Virgo and Kagura. But it's a very rich story with the sources and the types of signals that we can expect. So to make this visual, let me remind you that that electromagnetic waves come in different wavelengths, and this is showing schematically that radio waves are long wavelength. At the intermediate part of the spectrum, we have the infrared, visible, and ultraviolet light. And then at shorter wavelengths, we have X-rays and gamma rays. And remember that electromagnetic waves also act as particles, and the photons that are particles of light have high energies when they are at X-rays and gamma rays. On the other hand, neutrinos are particles, definitely particles, and they are neutral. Cosmic rays being charged particles, as we have heard, and travel a twisting path when they're acted on by magnetic fields. However, in the limit that they're more energetic, they can be also straighter. So And gravitational waves are distortions of the space-time geometry, which you've just heard Peter Fritschel describe how we've learned how to detect those. And in fact, in motion, the gravitational wave is a stretching and squeezing that elongates in one direction and squeezes in the other, and then reverses that. Okay, so these are ways we can learn about things. As I mentioned, if the cosmic rays go to higher energy, and maybe in the limit of extremely high energy, they become straighter and can point back to a source. But lower energy ones are more convoluted. So multi-messenger astronomy is then the combination of two or more of these types of signals to learn about astronomical objects. The picture I have here of a gravitational wave oscillating is a two-dimensional version of that, which gives you some idea of what happens at one point in time. But to see what the waves actually look like in 3 dimensions, here's a view of the that kind of wave motion, but traveling through space from right to left. In addition, so at any given part along its path, there's this stretching and squeezing that deforms a circular ring into an oval. But as it goes, it also carries a wavefront. So gravitational waves can be produced when a lot of mass changes its shape or orientation rapidly. It's a different type of process than producing light or producing particles such as neutrinos or cosmic rays, in that it really comes from the gravitational effects captured by the general theory of relativity, and how the change of the distribution of mass or energy causes the distortion which propagates away. To give you an example, a very important source of gravitational waves would be a pair of objects that could be neutron stars or black holes. And as you've heard, we have actually detected some of these. The key thing there is that when they orbit each other, they are, it's the distribution of mass is rapidly changing as they get close together. And that then produces a gravitational wave strain, a space-time distortion, which travels away. And some distance away from that, there would be this stretching and squeezing action in the geometry of space-time at that point. As Peter Fritschel mentioned in the previous talk, this is described by a strain, in other words, a fractional stretching or shrinking. And we usually use the symbol h to describe that, but it's the length change divided by the length. So these two objects are changing with the same shape, even though one's twice as large as the other. So the absolute length change of one is twice the other because its size is twice as great. On the other hand, if these are radiated from a source, such as a binary system, when they are farther away, they get weaker. Because h is an amplitude of the motion, h is inversely proportional to the distance from the source. And so the farther away you get, the weaker the wave gets. And even though these are very violent, powerful events where they occur, since they are very rare in the universe, most of the ones that we are aware of have happened very far away. And so by the time the gravitational wave gets to Earth, that's what makes the strain amplitude very small, and of order 10 to the minus 21 is a typical size of a signal. And it may be even smaller for a more distant event or an event that's intrinsically weaker. The growth of the network here has been just wonderful over the past. Really, it's come together as an advanced network with construction, installation, commissioning, and our observing runs in the last decade. So it's not an old science in terms of our advanced capabilities, but it built on the many years of work before that. So the six sites shown here represent sites for the Ligo scientific collaborations, the Ligo detectors, and Virgo and Kagura. The geodetector is part of the Ligo scientific collaboration. So it works most closely with the Ligo project, but all of these, the 3 collaborations represented here, although they are separate collaborations with their own organization and governance, We all work very closely together, and especially on the analysis of the data that's collected, but also on detector technologies and running schedules and so on. So, so it's a worldwide effort, but it is a coordinated worldwide effort. Let me just review some promising sources. First of all, binary black hole systems. That was the first signal that we detected. And you've seen one version of how the signal looked in Peter's talk before now. GW 150914 was this merger of two binary black holes. And in the data from the two LIGO detectors, which were operating at the time, you can see about 6 or 7 wiggles in the data. And remarkably, you see them in both detectors, and with a little bit of shifting and flipping, which makes sense for the signal, they line up. And they didn't occur at exactly the same time. They occurred 7 milliseconds apart, which is one of the pieces of information we can use to reconstruct the direction that the signal came from. If this data is plotted as a spectrogram, so an intensity represented by color as a function of time and frequency, then you can see how over the duration of the signal here, it rises from a low frequency to a high frequency and then cuts off. And the strongest signal is well, it's getting close to its highest frequency. And you can see a similar shape in both the detectors. All right, so that's one of our promising sources, again, because there's a lot of mass in the two black holes orbiting each other. Binary neutron star system works the same way, but because the masses of neutron stars are smaller, they're still greater than the mass of the sun generally, but they're smaller than black holes. This process occurs more slowly. So the orbit progresses more slowly. The neutron stars orbit each other many more times before they finally come together and merge. It can be thousands of times within the frequencies that LIGO and Virgo and Kagura can detect. So only the last part of it is shown here. But it's the same idea that you see the signal rising in frequency and rising in amplitude until the merger occurs. So those are well-known sources, but let me talk about a couple of other things. The core collapse of a massive star. High mass stars do often end their lives, their relatively short lives, by undergoing a core collapse supernova. The core collapses when it doesn't have enough pressure to support its expansion. And if that happens in an aspherical way, that can produce gravitational waves. A purely spherical collapse would not produce gravitational waves because that is not a mode that couples to the wave polarizations that Einstein's general theory of relativity tells us are allowed. So it would not produce a signal that would be carried away. But although a star is roughly spherical, stars often are rotating, and especially as they collapse, that can speed up the rotation of the core. So that is one of the effects that can cause the collapsing material to flatten. And if it flattens like that, then the difference between the horizontal size and the vertical size produces the difference that can create a gravitational wave in that final collapse process. There can also be gravitational waves caused when the material falling together reaches such a high density that it stops the collapse and it can even bounce. It's extremely high density at that point, but that bounce can produce a gravitational wave signal. And also the material that continues to fall onto the core as it's building up mass, this very dense core, can cause it to oscillate. And that can produce gravitational waves that radiate away and have a distinctive signature. So there are different ways that a core collapse can produce gravitational waves that have different signal characteristics. We generally call this a burst source, meaning that it's a transient source that lasts for a short period of time. And we are open to different, we don't think we know the exact waveform. So we design methods that can detect different waveforms, different signals, but of this type. And the last one I want to highlight here is a rapidly rotating neutron star. If it's not symmetric around its axis as it rotates, then it will produce gravitational waves with that rotation. And we call these continuous wave or CW gravitational waves. So these are not all of the possible signals. We search for others too, and some of the we do have a handful of papers, maybe about 10 papers still to release from and analyzing the O3 data, and many of them are searching for these types of signals. But most of these other types of signals these have not been detected yet. Our detections have been of the binary mergers. So with these astrophysical pictures of sources of gravitational waves, some of these are also expected to be multi-messenger sources, and we understand the mechanisms for that. For instance, when a binary neutron star system spirals together and merges, in the final stages, the tidal effects from the gravity of the two neutron stars close together cause some of the material to be ejected, and so you can see this disrupted material in this animated simulation coming out together. Also, when the cores collide, there can also be an outflow of material kind of from that collision too. So there's material around the remnant. The remnant itself might be a heavy neutron star, or it might promptly collapse to be a black hole, depending on the masses. But the material that's left over around that can fall back and make a disk around it, an accretion disk. And through the rapid accretion around this remaining object can produce a relativistic jet. So highly relativistic particles that come out at the two sides along the axis, the rotation axis here. And jets like these are the cause of gamma-ray bursts. And so that's a signal that can be accompany the binary neutron star merger. Gamma-ray bursts, when the jets travel out into the interstellar medium and interact with the tenuous material there, that produces electromagnetic signals at many wavelengths, which is called afterglow. And because we have highly energetic particles in a jet like this, there can be interactions that produce neutrinos. So there could be a neutrino signature from this too. On the other hand, some of the material that's ejected just flies away from the binary, and as it does, it started out as basically neutrons, but the newly freed neutrons can collide and decay and produce protons and electrons and start to do nuclear reactions. So in a matter of a fraction of a second or a couple of seconds, there are many nuclear reactions that occur that produce heavy elements, which then expand at a high rate. And this expanding cloud of elements, this mixture of many things, includes many heavy elements that are radioactive and decay. So even as it's expanding, decays of those heavy elements are providing additional heat. They're heating up the expanding material, and that glows. There's a thermal emission from this cloud as it expands. This is called a kilonova for historical reasons, and connecting it with but it's an optical transient. It's something that can be seen for a short period of time. So those are some great connections that you can see with gamma rays, with the afterglow can be in X-ray and radio and even optical. We have an optical signal here. In and around the visible band, we have neutrinos, so all sorts of different possible combinations there. In the case of a core collapse of a high mass star, there are nuclear reactions going on that are a large part of the energetics at that time, and so neutrinos are streaming out of a star, and so those can be detected. The outside of the star, the envelope is expanding then and creates the bright supernova that is what's observed in telescopes, and the shocks that are formed here can also be a source of cosmic rays acceleration. And then one of the other highlighted sources, a rapidly rotating neutron star, can give us pulsed radio, X-ray, or gamma ray emissions, and so that would be known as a pulsar, and that would be another messenger besides the gravitational waves that could come from that. All right, I didn't mention binary black holes. There has been a hint once, basically for the first one, of a possible gamma ray signal, but we have not seen that for other binary black holes. So we don't think that binary black holes are sources of other emissions that are detectable because they're mostly very far away. but perhaps an occasional one could be, so we continue looking for that. All right, well, with these different messengers, they carry different information about the astronomical sources, and that's one of the great things about using them together. This is a very busy slide because, well, on the one hand, I'm just showing some examples of astronomical instruments of different type, from missions in orbit that detect gamma rays and X-rays, to conventional but very powerful telescopes on the ground, visible light telescopes or infrared radio telescopes, and to neutrino detectors too. And each of those types of detections has their own strengths that tell us different things about the source. Or turning this around, you could say that we get different views of the event. We get information about the core engine, the thing that really drives the event, from gravitational waves and from low energy neutrinos in the case of a star collapse. We get information from the outflow of material that would be in a supernova, for instance. It could also be neutrinos as well as light, or the jets that produce gamma rays and then X-ray and radio afterglow. And we get information also about the environment in which this occurs from some of these signals. So besides multi-messenger astronomy of identifying these signals that are arriving, we can start to learn about the astrophysical properties of these sources. So it's also called multi-messenger astrophysics. All right, we have done many searches already with for multi-messenger searches. Many of them have not detected a signal, but we've done the searches nonetheless. Ligo and Virgo have published many papers trying to find signals, and now that we're collaborating with Kagura too, we're continuing. But searching for gravitational waves at the times of reported gamma ray bursts and at the positions in the sky of known pulsars and so on has given us many targets to go after. On the other hand, sometimes we analyze the data together and we try to find a weak signal in combination with these. Besides just using the observations that astronomers have already been making, we started a program of providing rapid information about gravitational wave event candidates to astronomers so that they could follow those up and try to find a corresponding source with the information that we're able to provide about the timing and the sky location and maybe the type of the signal. And so you can see schematically that this is collecting data from the different detectors. We've done this so far, this operation with Ligo and Virgo, and in the future we'll be using Kagura and Ligo India as well. We collect the data and analyze it and figure out where in the sky it would come from if there is a potential signal. And then we have some selection criteria on those and do some checks and send that information out to observatories to give them targets to go after. And we have done that for the last few observing runs. All right, well, you've seen one version of this already. This is, again, the 90 or so compact binary mergers. This is all of the signals that we've detected in gravitational waves. They're all compact binary mergers. And in chronological order, you can see the 90 events. The two lower dots in each case are the masses, the initial masses, and then the upper dot is the final mass of the merged product. Blue means black holes, orange means neutron stars, and you can see that the neutron star masses are typically 1 to 2 times the mass of the sun here. And then there are some ambiguous cases where we know that the masses are a few times the mass of the sun, and we don't know whether there should be neutron stars or black holes, to be honest. But we do measure we do see the mass there. And we've already heard this highlighted briefly by Peter Fritschel. Our first binary neutron star event, you can see the 2 orange dots here, was GW 170817. That was fairly early, but after we had detected several black holes. And that was just spectacular. If you know the story about this, it's still nice to relive all of the different ways that this event told us about told us many things. It was found in rapid analysis and low latency analysis of the data, and it appeared to be a binary neutron star system. And in fact, we knew within minutes that there was also a short gamma ray burst at almost the same time. It was about 2 seconds apart, detected by the Fermi satellite. The signal, when we plotted it, was easily visible in these spectrograms. So these are similar to the spectrograms I showed before for GW 150914, except the time scale here is much longer. This is now 30-some seconds from side to side. So this is much slower that the signal rises in frequency. But along this track, you can see that it stands out visibly in these signs. So this meant it was a strong signal. And because it was a strong signal that helped us locate it in the sky, in fact, we were able to pin it down to 31 square degrees, which is very good for gravitational wave detectors, especially with only 3 at the time. We'll get better when we have more in the network in the future. And we could estimate the distance. So that's information that we provided. But one of the interesting things about that is that our localization was really helped by Virgo, even though, as you can see, Virgo didn't detect the signal. Well, you don't see it visibly, but it also, in a deep analysis of the data, it was barely there, if at all. But that turned out to be important. With just the 2 LIGO detectors, we could only localize it to these 2 arcs that are shown in blue, which is a pretty good small part of the sky. The key was that we're combining the signals detected by these 3 instruments with their sensitivity to different directions. The LIGO Hanford and LIGO Livingston sky maps or sensitivity directions were, they're fairly sensitive in this direction. But in the case of Virgo, the Virgo sensitivity pattern on the sky had directions where Virgo was very sensitive, that's in red, and 4 directions where Virgo is not sensitive along the directions of the arms. So this is a known feature of these detectors, and actually it's very helpful here because the absence of a signal in Virgo told us that it had to be occurring near one of these nulls, near one of these holes in the response where it doesn't respond much, and that's what led us to reduce the area to this little white region here. And in fact, that was consistent with what the gamma ray burst detectors were, Fermi GBM, which gave us this purple area, and then combining that with the integral satellite, which saw a weaker signal, but at about the same time gave this gray band. So it all fit together. Also, another interesting thing that you already know about this is that this signal traveled for 140 million years to get here, and the gravitational waves and the gamma rays arrived within 2 seconds. So that tells you immediately that the travel time is just about the same. Now, they wouldn't have been emitted at the same instant necessarily. The theoretical range is in kind of plus or minus several seconds. So there's some range of relative times that's possible there, but we were still able to use that to say that gravitational waves travel at the speed of light to within a few parts per quadrillion, which we expected, but this was a great way to just directly see that. If it had traveled at a different speed, these 2 events wouldn't have happened at, maybe not even in the same year when it reached Earth. All right, well, having a location of the sky, we shared that information with astronomers, and within about 11 hours, 6 different teams found an optical transient that hadn't been there before. You can see it marked by crosshatches in these 6 traces here. So the image from one of them, I think Peter Fritschel already showed this once, but on the first detection, here is the image found by the SWOPE telescope. And the object that was new, was not previously cataloged. 4 days later, it looked like this. So here's August 17th, here's August 21st. And you can see that it's much fainter and it's much redder. And that's important. But anyway, so the galaxy here is known. This is called NGC 4993. Having this discovery pinned it down to a specific galaxy and even where it is in that galaxy at the outskirts here. So that's much more precise than we could do with gravitational waves alone. And that meant that it could be studied in detail by many people. A large number of the powerful telescopes of the world were looking at this object as much as they could for weeks or so. As it faded, as this kilonova cloud expanded, it became cooler and it became redder and it went into the infrared. You can see the blue and visible colors faded rapidly. Infrared lasted for weeks. And then later on, starting several days later, the first X-ray and radio signals were detected. And this brightened in X-rays and radio waves for months, for about 4 months, 4 or 5 months. You can see the rising intensity in radio, the rising intensity in X-rays, And then even at its peak, it was even seen as an optical afterglow by the Hubble Space Telescope. And then it faded gradually, and it's been fading since then. In fact, it has still been detectable in X-rays recently, up until a few months ago, or whenever the most recent detection I've heard of. It's very faint, you can barely detect it, but this X-ray is still fading away. There's even a hint that it may be brightening a bit also, which is something that had been suggested as a possibility. So this may have more to tell us about the expanding jet and the environment that it's expanding into, and some of the astrophysics there. All right, all these, I have to say that there was also a search for a neutrino counterpart, and there we didn't get we weren't so lucky that we got a neutrino counterpart too, but it was, we had instruments that could look at that. And in particular, the Auger observatory had it was very well placed for Auger to search for neutrinos that would skim the Earth and come out and be detected by the Auger detectors. And no signal was found there. But also the IceCube and Antares neutrino detectors found some possible candidates, but at around the same time, but nothing that seemed to be related. All right. One of the other wonderful things about this multi-messenger astronomy is that we're able to do nuclear physics with these observations. This confirmation of the kilonova picture and measurement of the light curves, the expanding cloud from this event helps to test models of that. And one thing that we've realized, that the community has realized in recent years, is that it's likely that a lot of the very heavy elements are produced largely in these neutron star mergers. The very heavy elements in the periodic table are produced by the R process. They have to rapidly capture neutrons to get past the kind of most stable elements. And so in this R process production of elements, there's been the question of where that happens. It can happen in supernovas. It can happen in maybe a couple of other places, but it's in the remnants of colliding neutron stars seem to be able to produce a lot of that. The details are still up in the air, and this is topic of research. All right, and one more thing I think here is that we can use this detection like this to check cosmology. Because the signal that we detect in the gravitational wave detectors has a connection with the distance, it gives us a measurement of the distance, although we have to make corrections for the orbital inclination angle and so on, which we don't necessarily know well. But we can make a measurement of this if we can get a redshift 2. We know the galaxy that it came from, and the galaxy's redshift is measured. Then we can use that to measure the Hubble constant. And so with this one event, we made a measurement of the Hubble constant. It's not a great measurement compared to the state of the art of other observations, but just for a start for gravitational waves, it was rather good, and it was in agreement with the Planck cosmic microwave background measurement of the Hubble constant and the supernova based measurement. This is a paper from a couple of years ago from our, it's not the latest information here. In fact, this discrepancy continues to be one of the really interesting questions in cosmology now. And our gravitational wave measurement is not answering, is not resolving this at this point, but we hope to be able to improve this over the years as we detect more signals. All right, so let me make a couple of comments about the 003 run and where we're going in the future. Breaking down the different runs, you can see that 03 was absolutely fantastic in terms of detecting events. 01 and 02 had some of our early breakthroughs, but in 03, we detected almost 80 new events. And those are, but the vast majority of those were binary black hole mergers. Which is great. We're learning about the population of binary black holes. You can see that there's one lone example here of 2 neutron stars merging, and a couple of interesting examples where a neutron star and a black hole appear to have merged, which I won't talk about. But let me just say a few words about this event, GW 190425. As you can tell, it occurred in April 25th of 2019. So it was a little under 2 years ago. No, a little under 3 years ago. This was, a a good event in some ways, but we were unfortunate that the LIGO Hanford detector was not on at the time. It's not collecting data. So the data we have is LIGO Livingston and Virgo. It was detected quite significantly by LIGO Livingston, but not a lot of information from Virgo. The signal appears to be there, but it's not very strong. And so we don't have much information about where it was in the sky. This is the entire sky, and you can see that it's really not pinned down. And in fact, no counterpart has been found for this event. So many astronomers tried to find a counterpart using the information we were able to provide, which wasn't very specific. And there were a lot of circulars of information reporting on their observations. There were definitely candidate optical transients found because those are very common in the sky. But follow-up observations of those found that they were typically supernovas and not likely to be related, not thought to be related here. It's not too surprising. The sky map was so large that we couldn't really say where to point. The source was about 4 times as far away as 170817, which means that for an optical telescope or an electromagnetic telescope, it's 16 times fainter. And so it's more of a challenge to detect there. Also, given that this would have higher masses than the earlier one, we think that it would collapse more promptly to a black hole, and that would leave less matter on the outside to even produce a kilonova. So it would, and to modify it by irradiating it. So we think that it was probably fainter even intrinsically than 170817. And I should say that there was a report, a published report of a weak gamma ray burst detected by the Integral satellite. It's a little bit puzzling that there seem to be 2 pulses. They each have 3 or 4 sigma significance there. I would say it has not been thought to be strong evidence of a counterpart, but it's kind of inconclusive. It's in a way similar to that gamma ray transient that seemed to be possibly associated with the first binary black hole merger. All right. So what we're currently doing now is preparing for the 04 run. This should start within less than a year, we think. We expect LIGO, Virgo, and Kagura all to have improved sensitivities, which means we'll detect more events. We'll be able to localize them better because we'll have a better signal-noise ratio. And especially if it's close enough and the signal is strong enough in 4 detectors, that would give us a great handle on the event. We're making updates to our systems for issuing alerts in support of this. We're improving our analysis pipelines in some ways, trying to reduce the false alarms from noise that occasionally fool the pipelines. We're trying to improve our rapid classification and make it a clearer classification method, clear classes and simpler approach, more unified approach. We're also updating our systems for distributing alerts, communicating them to observers. And we're making improvements to the speed to try to get the alerts out sooner, including an effort to produce early warning alerts where we don't even wait for the whole merger to occur. If the signal is strong enough, we can see that it's headed to merging tens of seconds before the actual merger occurs. And so if we can identify that and act on it and get the word out, we could potentially get alert astronomers before the merger even occurs, with some information about where in the sky it seems to be coming from. There's a proof of principle kind of paper here that using some simulated signals, and you can see that they were able to get negative latencies, so negative times after the merger, in other words, before the merger in these tests. All right, so we want to be ready. I'm personally hoping that we get a few events, multi-messenger events in 04. We'll have to see what nature really gives us. Going forward, improvements for the future are partly about the electromagnetic and neutrino detectors. So in space, we have very capable missions now, but they are aging. It's not clear how many more years that they will be operating. There are some new space missions coming online recently or coming up soon that will contribute, so that's great. Even the premier space telescopes can be used once a counterpart has been found, and like Hubble was used for 170817. Beyond about 4 or 5 years from now, it's not so clear what missions will be up in space. And there are several concepts that are being developed now and being proposed. So hopefully some of those will be picked up. But many missions now recognize the multi-messenger aspects and can contribute to that. So for instance, the COSY mission that was recently selected by NASA has some capabilities that will be interesting for multi-messenger astronomy. And on the ground, there are lots of things in the works. I'm just highlighting a few of the major projects here. The Vera Rubin Observatory, which is this very wide field of view telescope that will scan the sky, very powerful for finding transient things in the sky. The Square Kilometer Array in radio waves, and the Cherenkov telescope array, which we've heard about. On the gravitational wave side, we are working on improvements to the network. We're continuing to improve the existing detectors. There's a project called Advanced LIGO and another project called Advanced LIGO Plus, another one called Advanced Virgo Plus. Some of the work has been done already, and further work will be done to complete those over the next few years to make the LIGO and Virgo detectors more capable. And then Kagura is continuing to commission, and in the next talk, Tagoshi-san will tell us all about that. So I'll leave it to him. But even later in this decade, we're talking about further upgrades that can improve these detectors even a little bit more. And another big development will be when LIGO India comes online later this decade. So that'll give us an additional LIGO detector. It's basically that extra LIGO Hanford detector now moved to India to a new observatory. There are also projects underway to develop and plan for more capable gravitational wave detectors at new sites. So even longer arms, and new technologies that will give them higher sensitivity. Just the names of these are Einstein Telescope, which is a European centered project, and Cosmic Explorer, which is a US centered project. So these detectors will have really great capabilities to go out to cosmological distances and detect binary mergers, as well as other gravitational wave signals. All right, so this is the second to last slide, but I wanted to just say, besides terrestrial interferometers that we've been talking about here, there are other gravitational wave projects that are in development or operating. So at very low frequencies with periods of years, radio pulsars are being monitored, and the timing of those is being analyzed to look for very low frequency gravitational waves. In an intermediate band, there are space-based interferometers under development. LISA and DeSigo are two of the leading, and Taiji and Tianqin are projects that are underway to put ranging spacecraft in orbit to detect the gravitational wave stretching and squeezing. And these will detect different types of sources, different astrophysical sources. So we'll have a more complete picture of the gravitational universe as these become mature and can detect signals. And I didn't, on this plot, doesn't include at extremely low frequencies, microwave background radiation, which there's the polarization mode called the B mode, which can be a signature of gravitational waves in the very early universe. All right, so to summarize, we're entering, in fact, we have now entered an era of multi-messenger astronomy and astrophysics. What we're doing is moving beyond the first steps for the gravitational wave multi-messenger to trying to do this routinely and to have many more signals. We need to improve the gravitational wave detectors and the gravitational wave network and expand it. We need to use the powerful tools of regular astronomy, high energy instruments and detectors on the ground. And when we do that, we can put these observations together and learn about the astrophysics of the sources, the properties of neutron star matter, nuclear physics, and test theories of gravity. So there's a wide range of science we can do. And with that, I'll end and just ask you to stay tuned, and we'll share the discoveries as we make them.
Can we ask questions? That was a terrific talk, Peter. Could you
thank
show
you.
us? Could you show us a? You didn't show us forms for the collapsar or for the cigar-shaped rotating neutron star. I know you
Yeah,
said they weren't that sound theoretically, but just to give us an idea and talk about how you would even see that they had happened, especially the cigar spiraling neutron star. That just seems like being continuous. It would just be sort of the background.
Right. I missed a few of the words you said, but I think I heard enough to think you're talking about this slide. And if you were asking first about the collapsar, the collapsing high mass star, so I tried to hint with the different arrows here that it's going to collapse more rapidly along the rotation axis than around the equator here. And that's because I'm imagining that it's rotating rapidly. So there's a centrifugal.
No, I see why there can be a signal, but I wanted to know what you think the signal would look like.
Oh, yes. Okay, fine. Okay, so in this case, from the side view here, you would get a linearly polarized gravitational wave that would be just kind of a pulse, because this collapse process would kind of grow the asymmetry, and it's this fourfold asymmetry between polar and equatorial. And so you get kind of a pulse from that. Well, it kind of, as it falls that way. So that part of the signal would be kind of pulse-like. The bounce also would tend to give a pulse unless there might be multiple bounces. For a rapidly rotating core, you can kind of get a centrifugal bounces and get a few bounces from that. So I don't have a picture to show of it, but you tend to get a waveform that's kind of like a pulse and maybe a few other little wiggles after that. For that kind of effect. On the other hand, if you get infalling material that's falling onto the core and the core is being driven into oscillation by that, then you get kind of a growing oscillation. So some of the simulations show that the protoneutron star starts to oscillate a fraction of a second after the initial collapse, and that can build up over the course of a second or so.
And what do you think the prospects are of seeing one of those, of being able to identify it?
Well, that's the key question, right? So another way to say it is, how far away could we detect one of these? Roughly speaking, we think we could detect gravitational waves from a collapsar in the Milky Way. Now, depending on the actual emission, it might only be a fraction of the Milky Way. It might only be within a few kiloparsecs of where we are, or for some of the other scenarios, it might be the entire Milky Way, but not extragalactic, at least with the advanced LIGO, Virgo, Kagura detectors we have now. With the third generation detectors, I think it's still a stretch to reach to other galaxies. So we're basically waiting for something to happen in our own galaxy, and we want to be ready when it happens.
Thank you.
So that's one question. In terms of the rapidly rotating neutron star, this is also something that you can estimate because neutron stars have got to be almost round. So it's a question of how far out of round they can be. But this is the kind of signal that we hope to detect out to some kiloparsecs. So this is also would be a galactic signal. But in this case, we know that there are, 1 billion or 10 billion neutron stars in our galaxy or something like that. Only some of them are going to be rapidly rotating, but there are a lot of potential sources in our galaxy, and they're there all the time.
Okay. Let's thank the speaker. And let's move to the next talk. The final talk is entitled Status and Future Prospect of Kagura, given by Professor Hideyuki Tagoshi from ICRR. Professor Hideyuki Tagoshi, please. Now.
Okay, the slide is okay.
Yes.
Yeah, okay. So, yeah, so I'm going to talk about what status of Kagura. So, since in the previous two speaker talk, very nice and introductory reviews were done about gravitational waves. So I think that we just go to some details Ligo Virgo have already produced a number of important scientific results. First, gravitational wave signal, GW150914, and first binary neutron star signal. And then for that, multi-messenger observations are done, successfully done. And then now, up to now, about 90 confident detection of signals are done. And just after 2 years from the first detection, these 3 people received Nobel Prize. Okay, and then what do we need for the next breakthrough? That's the thing we want to consider. And so since the theme of this symposium is a multi-messenger, so then let's talk about the multi-messenger things. And so far we have only one confident electromagnetic counterpart detections, as Peter Shawan mentioned, explained. So, and then what is necessary to observe EM counterparts? So one thing is, of course, the improvement of sensitivity of detectors. So then this effort is ongoing at each gravitational wave observatories, and sensitivity is continuously being improved in the past. But the other thing is improvement of source localization. And so these sky map are also shown by Peter already, but just briefly come back once again. Left figure is a sky map for the first binary neutron star event. And the right figure is a sky map for the second binary neutron star event. And in the left figure, this green region is a region of the source location determined by the gravitational wave detectors. And here sky map means the error region of the source location, and means the possible location of the source in the sky. And for this case, initial sky map is about 30 square degree. And but on the other hand, for the second binary neutron star event, so the initial sky map is 10,000 square degree. And so this is primarily because this observation was a 2 detector observation with Ligo Livingstone and Virgo. And Hanford detector was offline at that time. So on the other hand, for first BNS event, it was a 3 detector observations. So we got this very accurate sky location, and then optical counterpart could be found, can be found. So then it's important to determine the location of the source accurately so that astronomical telescope can perform follow-up observation to search for the optical counterpart. But one laser interferometer cannot determine the location of short duration source in the sky. So that's because so these laser interferometer signals from different directions are received with the detector in the same way and cannot be distinguished. So it looks like the same, even if they come from the different direction. So one detector cannot determine the sky location. We need 3 or more detectors to determine the source location accurately. So gravitational waves propagate in the space-time and arrive at each detector, but at a different time. So arrival time of signal at each detector is different. Difference depend on the location in the sky. So with 3 or more detectors, the direction of the source can be determined. Of course, there are some other factors to determine the sky location. Laser interferometer have some direction dependence of the response. So that is also useful to determine the direction. But we need 3 or more detectors to determine the sky location of the source. And then the other thing is that the duty cycle of gravitational wave detector is typically about 80% or 80% or 90%. So it's not 100%, it's less than 100%. And there will be downtime for each detector, even in the future. So that cannot be avoided. Then if one detector down, then if there are only 3 detectors and 1 detector down, so only 2 detectors are operational. But if there are 4 detectors, even if 1 detector is down, we still have 3 detectors and the source location can be determined. So to have 4 or more detector is important. So that's the point. So then, I'm going to explain the Kagura. But before that, I just want to mention the previous detector in Japan, which is Tama 300. This, which was briefly mentioned by Peter Fritcher. And so this detector was 300 meter detector and a Fabry-Perot microsome laser interferometer, and which was built at the National Astronomical Observatory of Japan in Mitaka, Tokyo. And this is the detector arm is built here. It's slightly underground, but it's not completely underground. And Tama 300 performed. Its construction started in 1995, and it performed 9 observing run from 1999 to 2004, and total length of data taken was more than 2,000 hours. And these initial papers we published. And then after that, in Japan, we started the request of the funding to the government, but it took several years until this Kagura detector was approved. And Kagura is a detector, laser interferometer detector, built in the Kamioka mine, and which is within the same mountain of Super Kamioka. They will come around Xmas for those scientific facilities. It's in the same mountain, but in different tunnels. So tunnels are built, excavated newly. And so Kagura is hosted by ICRR and as a main host, and as a cooperative institute where NAOJ or KK and many universities are involved. And okay, and the location is here. This is Japan, and here this is nearly the border of Toyama and Gifu prefectures. And yes. Okay, and its design sensitivity of Kagura is almost comparable within the frequency region of near 100 Hertz, which is a best sensitive region of the detector. This shows sensitivity spectrum. Horizontal axis is a frequency, and the vertical axis is a strain noise spectrum density. Okay, and so red and blue are the two possible design sensitivity of Kagura, and green Virgo and black advanced Ligo. Well, this is a bit old figure. Yeah, but around here, all 4 detectors have the similar sensitivity. And then I briefly explain the history of Kagura. Well, in 2010, the project was approved by the government. And next year, tunnel excavation were planned to be started, but it was postponed due to the big earthquake on March 11th, 2011. And then 1 year later, tunnel excavation started, and in 2 years later, 2014, it was finished. And then construction of the facility inside the tunnel were done, and it was almost finished in 2015. Then commissioning, building detector, construction of the detector itself are done. And in the next year, 2016, first operation of the 3-kilometer Michelson interferometer were performed. We call this as an ICRR operation. And so, and then later, 2018, first operation of the Michelson interferometer with a cryogenic mirror performed. Then in Kagura planned to join the Ligo Virgo third observing ground. For that purpose, memorandum of agreement between Ligo Virgo and Kagura was signed in October 2019. And then in joint observing ground with Ligo Virgo could not be realized, but instead, first joint observing ground with GEO 600 in Germany were performed in 2020. I will come back with this later again. Okay, and then I briefly explain why underground. Well, Kajita-san already mentioned at the first talk, but since gravitational wave detector is a very sensitive detector, so we need a quiet environment. So this figure shows a seismic vibration level, seismic vibration spectrum. And so horizontal axis is a frequency, vertical axis is a seismic motion. And well, the blue one is a seismic motion level at the Kagura site. And the green one is a seismic motion level at the entrance of the Kagura tunnel. And the red one is Tokyo. So as you can see, so blue one, seismic motion within the tunnel is smallest. So in a way, it's even better than the entrance of the tunnel, around 1 to 10 Hertz. So, and entrance, the seismic motion is better than Tokyo within 1 to 10 Hertz, but at a higher frequency, it's a similar level. But within a tunnel, but it's still better. So yeah, this is one advantage of the underground environment. And second important feature of Kagura is Kagura uses cryogenic mirror for main test masses. And so this is a cryostat. And within the cryostat, the suspended mirror are located. And this mirror is cooled down. And this cryogenic mirror, our cryogenic mirror is a sapphire mirror, and with this size and 22 kilogram. And so this cryogenic mirror, this is a very particular feature of Kagura detector. And so yeah, this underground environment and cryogenic mirrors are some advanced, these are the advanced features. So Kagura is sometimes called a 2.5th generation detector. Well, advanced Ligo and advanced Virgo current detectors is called second generation detector. Okay. And so, yeah, tunnel excavation finished 2014, and this is the entrance of the Kagura tunnel. And yeah, so for installation, this vacuum tube carried into the tunnel, and this is a cryostat. Yes, this is some digital computers. And this is a current view of the Kagura tunnel. So these vacuum duct, vacuum tube are installed. And for one arm, 250 ducts are installed. For each arm. And this is what central area, and this is a installed cryostat. And one issue of the underground environment is that spring water from the wall. So in order to avoid such water, the wall were covered by the waterproof sheet. So yeah, this is a current central area of the detector. And yeah, we have a outside research building. These are called data analysis building, and some people's room and control room and computer rooms exist. And the control room is located here. And it looks like this. Okay, and this area is famous for the some snow. And so in the winter, it becomes something like this. And recently, maybe because of the global warming, we don't have much snow, but this year we have a lot of snow. So. And then, yeah, in October 2019, Ligo, Virgo, Kagura memorandum of agreement are signed. So this is a picture of the ceremony. And then Kagura formally joined International Gravitational Wave Observatory Network. So then after this ceremony, in February 2020, Kagura was trying to join Ligo Virgo third observing run, which was started in April 2019 and planned to continue until the end of April 2020. However, on March 26, 2020, Kagura achieved the sensitivity which is good enough to observe binary neutron star coalescence at 1 megaparsec. And this sensitivity was a criteria that Kagura have to achieve in order to join Ligo Virgo 03. So we achieved it. However, as you know, at that time, the COVID-19 pandemic was spreading quite rapidly around the world. And yeah, it becomes really serious in US and Europe. And then in March, Ligo Virgo decided to stop the observing run, and they stopped the operation on March 27. So well, initially it was supposed to continue until the end of April, but it was stopped. So thus Kagura lost partners for joint observing run. However, fortunately, we learned that GEO 600 in Germany was operational even in this pandemic. So GEO people agreed with the joint observing run. And after some discussion, joint observing run by GEO and Kagura was approved as a joint observing run within the framework of Ligo Virgo Kagura. So, so then for Kagura, this became the first international joint observing run. And the run was performed from April 7 to 20. And for 2 weeks. Later, this joint observing run was named O3GK. And several data analysis to search for gravitational wave signal have been performed, and the research paper is now under internal review. And so, unfortunately, so I cannot tell much about it, but it is planned to be released very soon. Okay, and so this is our evolution of the sensitivity of Kagura. Well, actually, this figure was also shown by Kajita-san too. So this is the initial Kagura sensitivity in 2016. This was at this level. This is horizontal axis is the frequency, vertical axis is amplitude noise spectrum density. And initially here, and March 2020, it becomes here. So more than 5 or 6 orders of magnitude improvement were achieved in 4 years. So, okay. And then, next to Ligo Virgo Kagura observing run, 04 is planned to start in mid-December of this year. And Kagura will join 04 from the beginning. And upgrade back toward 04 is in progress. However, expected sensitivity of Kagura at 04 is still not so great compared to Ligo Virgo. And we announced the start date of the 04 and expected sensitivity publicly. So Ligo is the sensitivity and Virgo sensitivity is something like that, which are better than the 03. But Kagura, we expect about 1 to 10 megaparsec. So 1 or 2 orders of magnitude lower than Ligo Virgo, but we will continue our effort to achieve better sensitivity and to achieve the design sensitivity. Okay, and then so when Kagura joins the network, then what we can expect for the sky localization accuracy. So this is that figure. This is a whole binary neutron star event. And also blue dot curve is only Ligo Virgo 2 detector case. And compared to that, if Kagura joined, then we have this accuracy. And so median, if we take median, it's a factor of 2 improvement can be expected. And of course, and if 4 detector operation is possible, then even better improvement can be expected. By the way, this is a bit old computation. Assumed sensitivity for Ligo is 120 megaparsec, Virgo 60, and Kagura 25 megaparsec. And so, by the way, first BNS event, the sky localization accuracy is about 30 square degree. But if we realize the design sensitivity, so even for the binary neutron star to 180 megaparsec with 3 detector, 30 square degree is achieved, and with 4 detector, including Kagura, it's about 10 square degrees can be expected. So there, and for black hole neutron star case, it's a similar improvement can be expected. So these are very good. Okay, so as Peter explained in details, so binary neutron star coalescence considered to be the progenitor of the short gamma ray burst. So we may gamma ray burst after the coalescence of binary neutron star it is produced maybe along the the direction of the jet produced after the coalescence. But kilonova produced within the merger ejector may be also produced. And this kilonova can be observed from any direction. So this is one of the targets for the multi-messenger observation of the binary neutron star coalescence. And then, another target for Kagura is a supernova. So in the Kamioka mine, we have a super Kamiokande detector, which is also the detector of ICRR. And so when supernova happens, then neutrino will be emitted, and gravitational waves also may be emitted if the core collapse occurs aspherically. And then, so coincident observation of neutrino and gravitational wave may be very powerful tool to explore the explosion mechanism of supernova. And so these detectors of ICRR can contribute a lot for such an observation. But these are possible if supernova occur near the galaxy, well, within galaxy, which are expected to be once in about 50 years or so. And this is the final slide. So in the next several years, we can expect many compact binary coalescence. So because of the improvement of the sensitivity of detectors, and Kagura will be catching up in the future. So maybe binary black hole coalescence once per day, or binary neutron star coalescence, I don't know, but maybe once in a month in O4 or so. So with this observation, many physics and astrophysics can be explored. So we are expecting very exciting area. That's all. Thank you.
Thank you very much. A question. There's a question in the Zoom chat. Professor Taguchi, can you see the question?
Yes. Those earthquake interpreting observation, especially in Japan. That is yes. Answer is yes. Yes. When big earthquake occurs, that cannot be absorbed by the seismic system, suspension system. So earthquake interrupts our observation. That's true.
Any questions? More questions? Oh, one. Okay, Glennis, please.
Thank you. Thank you for that nice talk and the marvelous experiment you guys will be having on your hands. I wanted to understand though, Kagura, one would think would be better than Ligo and Virgo since it's generation 2.5 and has the advantages of being underground and the cryogenic thing, and yet you're still quite a bit away. And I wanted you to talk about what the things are that you have to overcome. Were there sort of unexpected problems, or is it just that it takes a long time?
Well, I think that the main reason is just the schedule is so tight. So we, why sharing was stopped? I don't know. Okay. Since the first operation, yes, this one. Yeah, first operation is 2016, and only 4 years have passed. No, now it's 8 years. So yeah, it's just taking time.
Have there been issues that you didn't anticipate, or is this the schedule you always expected?
Yeah, well, yeah, yeah. Schedule is always tight. So yeah, and what is the question? Sorry.
I wondered if there had been problems that came up that you didn't expect, that were harder to solve than you thought.
I think so. Yeah, maybe it's a very detailed, but there are very detailed problem happening. That's always happening. I think it's the same for all of the gravitational wave detectors. Yeah. So yeah, so in order to solve these detailed problem, yeah, it's taking time. Yeah.
Any other questions, comments? Oh, one more.
Is it about quantum noise?
Yeah.
No, these problem are not a quantum noise, yeah, but more practical noises. So quantum noise is a very, very fundamental noise, but before that, we have to reduce the practical noises. So currently, those are the issue.
Any other questions or comments? Okay, if not, let's thank all the speakers. Okay, finally, Professor Takaaki Kajita will give a closing remark. Professor Takaaki Kajita, please.
I would like to thank you all, researchers and the general public from around the world for participating in the event today. To commemorate the major renovation of the University of Tokyo New York office in 2020, the University of Tokyo invited applications for the University of Tokyo New York office events. And today's event was chosen as one of them. We'd like to thank the staffs of the University of Tokyo and the New York office for their support in organizing this event. We had originally planned to have a hybrid event with the New York site. However, as you know, considering the situation of the recent COVID-19 infection, we decided to hold the event completely online. I hope that today's event will be a good opportunity to further promote interactions among researchers and to attract the general public to astrophysics and to know the University of Tokyo New York office. Now, we close today's symposium. Thank you very much for your time today.
Thank you very much. Now we will close the event. Thank you all. Have a nice evening, everybody. Bye-bye.